Welcome to the tutorial on answer set programming from theory to practice. My name is Torsten Schaub, and as I try to explain while being muted, thank you for all the notes, by the way. I will be trying to use a pen. That's me here, Torsten. And this pen and the mouse will interact, and let's see a little bit how this goes, right? So let's first of all look a little bit what all this is about. So this is more or less the outline and of today's tutorial, right? So we have 3 hours, actually less than 3 hours, because we will make at least one break, I guess, at some point. And we follow more or less these seven topics. I think more or less we will be doing quite a lot in the beginning in terms of where's my mouse actually? Should be there. At the beginning, oh, there it is. This will be a big bulk here, where we talk about ASP, what it is, what it does, then look a little bit at the foundations. And then the other big bulk will be modeling. So once we more or less sketched a little bit how grounding works, how solving works, we will look a lot into modeling. And then last but not least, we will talk about engineering. And this is more or less the sophisticated part, where we talk about APIs, application programming interfaces in Python, and how we can actually extend the solver with new inferences, and also just treat the solver as an object and talk to it. And then if time permits, we will just see a little bit what we can do with these topics, and I will talk about at least my preferred application. Most importantly, again, I will just be hand-waving, sketching from time to time. If you want to go a little bit deeper, we have actually much more teaching material here at this site here, where this material actually is sitting a bit more distributed, because there it's a full course in a master program that we are using. And here, this is more or less only a part of that, right? But at least there's the full material, and this material is also, the material I will present you today is taken actually from this. Good. So let's get going. Let's first look at the introduction, and there, of course, motivation and introduce a little bit in the topic. So I will first talk a little bit about what is the general idea, then more or less what is ASP in a nutshell, and then this may be a first time to say, okay, now I understand what it is in a nutshell. I don't have to go in the details. Well, for those who then want to stay further, we look a bit at the historical development, because I think this is quite interesting to understand certain design decisions here and there. Then look at the workflow and how ASP is used. Okay, let me briefly look in the chat. Sorry for that, just to make sure that I'm not overlooking something. Yeah, it's mainly about me being foolish and muted. Okay, so motivation. So first of all, I think most of us are computer scientists, and also the idea with answer set programming is that it allows us to solve problems. And every program is doing it. But let's actually look first at traditional software. If we look at traditional software, well, we have users, then somebody has written a program, and this program actually is executed on a computer. And what this program does is it solves a problem for the user by mapping it on a computer, who then just executes the program. So the first thing to note is that this program was programmed by a programmer. And in traditional programming, the intelligence lies actually with this guy, right? So because the program is more or less a path to a solution. So, and this is hardwired in the program, how to obtain a solution. What is already interesting is that, to note actually, is that the program is domain specific, application specific. So the program has to express how to solve the specific problem, or at least the specific class of problems. That's actually what I want to indicate with this question mark here. So the program has to know about it. He has to be knowledgeable somehow to program things out. On the other hand, the computer, that's actually why I put here an ampersand. Well, the computer is universal or general in the sense that it can compute all computable functions, right? No matter what the program actually does in the end, computer doesn't care. It just executes it, right? There's nothing special at that point. Okay, then what about then knowledge, or let's say what we do here with our knowledge? The idea is more or less that we declare our knowledge and then use this knowledge actually with the intermittent of a solver to obtain a solution. Okay, how does that work? So my preferred expression is actually to say not only it's that you declare what the software should do, that actually it's knowledge driven. Okay, we have this part here. So this is more or less where we express our knowledge. Then a solver knows how to solve the problem, and then this is then mapped on a computer. And this is different in certain ways. Again, keep in mind that originally in the program described how to solve a specific problem. And this was domain specific. While here the idea is that only the knowledge about the problem, what is the problem, is domain specific, application specific. The solver as such is also universal or general in the sense it can solve all types of these problems. And here in our case, these are mainly combinatorial search and optimization problems, right? But the important thing is, it are two things. First of all, a program solves the how problem. It expresses how to solve my problem. How do I find a path to my solution? While here, the only thing that is given from a user, actually from an expert, is what actually is the problem. You just declare the problem. And then there is a general piece of software, a solver, that knows how to solve it, how to find a path to the solution. And this is, again, a universal thing, just as the computer. Of course, a computer can compute. This is why this is also larger here in the sense, all computable function, while solvers can more or less compute the type of problems they're designed for, right? In ASP, these are problems that go up to the second level of polynomial hierarchy. In SAT, you are at the first level. In QBF, you can take all problems up to P-space, right? So, but these are solvers. They know how to solve your problem once you told them what your problem is. But you only say what the problem is and not how to solve it. And that's the basic difference actually in an approach like ASP or answer set programming, which is the same as in constraint processing or in satisfiability testing a priori, right? So we all use these solvers to solve our problems, and we concentrate on declaring them, on just expressing the knowledge. And another actually not so subtle difference is that for the program, you need a programmer, you need a computer scientist. Well, here the idea actually is, and this is at least the idea in ASP, where you really want to represent your knowledge and you want to have a language where you can express it, that it's not necessarily someone with a computer science education, it's an expert. And actually, we have been experiencing this quite a lot, where we see actually how biologists, how even business people express their rules and then solve the problems. And this is something they can do without a computer science training. That's actually, I think, one of the big ambitions of ASP, to be that it's also usable right away for non-computer scientists, for experts in a certain domain. Okay, so what is the benefit? Again, this is now this knowledge-driven partition of knowledge and solver. First of all, the experts should do that. Actually, one can go even one way higher. One can actually express this knowledge in terms of natural language. And then actually, once you have it in natural language, not perhaps to write it down, but at least to understand what the system is doing, is accessible to a layperson. The good example is, so we are doing, with our company, we're doing shift planning for companies. And this shift planning problem is expressed in an ASP specification. And you can take this specification, compile it into natural language, and this is actually this is done mainly actually very nicely by Rolf Schwitter at Macquarie University in Sydney. He has tools for that. Then you get a text out of it, and with this text you can go to the union. You can say, look, this is what the shift planning system in the company is doing. Or perhaps if you have alternatives, you can present this all in natural language, and then they can, I don't know, criticize certain specification or not. But I think this is another dimension of transparency, in particular in this discussion of AI ethics and transparency, that I think is pretty cool. Okay, by doing that, so more or less putting down the knowledge in a specification, even with a natural language. But again, natural language is just one thing one could do. It's not really done a lot, because actually, as computer scientists, we just write ASP directly. We don't use natural language for that. But what we get is transparency, is easy to understand, flexibility. Normally these specifications are very short, right? So I was talking about shift planning. So I don't know, a simple shift planning problems can be pinned down on 2 pages. And this works for a company with legal regulations and all that, right? It's easy to change and to maintain. And if you really want it, since your object that you actually want to verify, it's pretty reliable. You can verify things, right? And we also have, actually, there are also tools for that. Okay, this is more or less about the ASP aspect that is more or less specific, that you really aim at putting down knowledge and not more or less knowledge at an abstraction level that at least an expert can understand it, and with some training also pin it down. So with a solver, here we come more or less into the area that is not only ASP specific, that applies to SAT or also to CP, right? These guys are general, they solve all the problems of a certain complexity class. They are highly efficient, right? SAT solvers, ASP solvers can solve problems of up to 10, 20 millions of variables. And again, this is not really the size of the problem. You have to think that if your variables are Boolean, then you can address problems with search spaces of 2 to the power of 10 or 20 million, right? In ASP, a lot of emphasis is also put on the fact that you can express objective functions, and at the same time, as you solve a problem, also look for the optimum problem. And ASP solvers are freely available. You can get them off the shelf. It's open source, just as more or less, I think all SAT solvers I know of, right? Okay, so this is more or less what you get when you follow this approach. And again, the upper part is, I think, more ASP specific, while the lower part applies to all declarative problem-solving paradigms, let it be CP, SAT, or QBF, or whatever, right? Good. Okay, so now what is ASP? I've been just talking about ASP, and again, it will not yet be clear afterwards. We will more or less get the precise definitions in the next chapter. So ASP stands for answer-set programming, right? No asynchronous server pages. I hope that no one drops out now. And it's an approach for declarative problem solving. And where does ASP come from? And actually, you can say that ASP has 4 models. And so database, in particular, deductive databases, logic programming, where actually the stable model semantics, which is the formal semantics used in ASP, comes from. It was originally proposed as a semantics for Prolog. Then knowledge representation, and notably non-monotonic reasoning. After all, we are now here in the at the KR conference, and this is where this comes from. And I think this is already a cultural distinction, for instance, of SAT, right? I think people that were doing satisfiability testing, they had their killer application in computer-aided verification. They did this a lot. No modeling language, more or less, was used. While, you know, when you belong to the knowledge representation and reasoning community, it's about how to represent knowledge. Modeling is important. Having a language for this is important. And I think this is also where this emphasis in ASP comes from. And then I think last but not least, I simply want to credit here the people in SAT solving who really push Boolean constraint solving to its limits. And of course, we benefit also from this a lot, right? Even though I think many ideas even go back to CP literature before, but they really straightened things out and made it highly efficient. Well, the other thing about these 4 mothers of ASP is, note that the first 3 actually are different from the last one, in the sense that databases, logic programming, non-monotonic reasoning all use closed world reasoning, right? Where the idea is, well, whenever something is unknown, you assume that it is false. Best example, of course, databases, but the same in logic programming, also in non-monotonic reasoning, right? While, of course, satisfiability solving works normally with Boolean logic, which works under the open world assumption. And we will actually see that this is, of course, one of the challenges in ASP, how to capture this closed world reasoning, how to capture that something is false unless you can show that it is true. Something, again, that is very common, I think, in common sense reasoning, but it complicates things. And this is actually why many people, when they look at the semantics, say, oh, this is complicated. Yeah, well, but you get something for it, right? We will see later on that what you get is you get exponentially more succinct representations over the same language. Anyway, so already pinning things down. So these are the first 3 approaches. So where's my oh, there it is. So the first, these guys here are actually all non-monotonic. Oh, my handwriting with this stylus is very bad. Monotonic. And this is one of the characteristics, one of the challenges actually when developing ASP. Good, then and they right away disappear. But you can more or less say that if you want to have the first nutshell, ASP is a combination of database techniques, notably techniques from deductive databases, logic programming, where the syntax also comes from, knowledge representation and reasoning, modeling, ideas from non-monothetic reasoning, and the computation borrows a lot from SAT technology. So here's the first nutshell what ASP is about. And actually, we will more or less deepen the different components on the way. Okay, so what is it good for? Well, as I mentioned before, right, it's good for solving combinatorial optimization problems. But what I think the unique selling point, the particular thing about ASP is it's very good for solving knowledge-intense problems because it has this nice modeling language in which you can model in a very elegant way. We will see this later on. Good. So what problems are there? Well, these problems consist of lots of decisions under constraints. And again, my standard example is these are all first world problems. I think all larger companies more or less have to cope with such problems, right? Let it be logistics where you have robots roaming around, logistics where you want to put items on a shelf that they're easily accessible, also depending on the season and stuff like this, right? Or timetabling, and of course Sudoku, right? Sudoku is, I think, a very nice illustration because you have to make decisions which digit to put under the constraint that you can't put a same digit in the same line, same column, or same block, right? And these are all the same type of problems in the same way as a computer can solve all computable functions. Here we can solve all of these combinatorial problems that involve many decisions under constraints. And here are again the examples, right? One of actually my preferred one is music composition. And we had a very talented master student who was actually studying music and computer science. And she developed a music composition in a master thesis. And again, it's more or less the same thing, right? You have these nodes, you have these nodes, and you can place each node at a certain point. First of all, you choose the node, which node you want to do, then where to put it, and then where to put the next node. And of course, the way you choose the nodes and you put the next one follows a certain pattern in certain music styles. And then depending on the style that you say, you encode different rules, and then you have different music then comes out, right? Feel free to go to our website to actually test this out. And otherwise, I think we have the standard combinatorial problems on configuration, diagnosis, planning, timetabling, etc., etc. Now you may say, oh, are these guys just toying around? Well, actually, meanwhile, there are also quite some industrial ones, and here's just a selection of them. Actually, those of you who run Linux may actually configure their system with our systems, at least in Debian and Ubuntu. The first killer application, or first really prominent application, I don't think ASP has a real killer application, just has lots of applications meanwhile, was done by NASA, actually by Michael Gelfond's group at Texas Tech, which was used for decision support for the space shuttle. And so one thing I didn't listen once we are also involved in train scheduling and these things. But the most interesting application, I would say, is actually the second one, where actually a couple of years from now, in the US, there was an auction on the radio frequencies, right? And I think, of course, what is always impressive is this number here, where they had a revenue of around $20 billion. And they actually used solvers to run this auction. And they actually used the portfolio out of, I think, Sattenstein developed in Kevin Leeton Brown's and Holger Ho's group at UBC, and actually clasped our solver, our ASP solver. Interesting, they more or less solved just, things could boil down to graph problems, and they actually used our ASP solver as a set solver, right? But it was more or less the most robust one, and it was better actually after optimization was happening than the available ones. But the more important thing with this is that they netted this. Actually, Kevin Leeton Brown was more or less doing this choice and doing this with a company for the US government, and they just chose our system. We were not really involved. And I think for a university group, right, or for university software, this is just a great story, right? So people go to your university website, download your software, and then the US government employs this in such a big project, right? And I think this just shows that the technology, meanwhile, as many other solvers in SAT and ASP and CP, of course, are very mature now, right? Even and I think they are the best ones of them are produced at universities and are freely available, right? And even such applications are done. I think that's a pretty cool story. Anyway, so if one wants now to sum up what ASP is about, I like normally to use these three bullets here. First of all, it has this high level versatile modeling language, and I think this is really the most distinguishing point. It has the other distinguishing point. It cares at the same time for qualitative and quantitative optimization, right? You can actually do both at the same time, combine things. So Pareto of lexico, you can just form an expression and then things are optimized. And of course, it shares with the SAT community and the CP community high performance solvers, right? So just that this is not an empty claim. Many moons ago, actually, we also participated in the SAT competition and we won them a couple of times. Well, actually 2 times, right? A real couple of times. So this is just to underpin that I'm not just hand waving and saying, oh, we're just as good. Well, we are at high with these guys. And I think they appreciate what we do just as well as we do what they do. Good. So these are, I think, the distinguishing features of ASP. And again, you will get to know them in what follows. And industrial impact, yeah, as I mentioned, right? So there are now the first companies, actually the people in Calabria around Nicola Leone have the company DLV Systems since, well, quite a long time. And we actually also a couple of years back formed Potasco Solutions. And it's interesting to see actually that it's, how to say, you know, to do marketing for a technology is more difficult than to do it for a project. For a product, I'm sorry. So if you have a product, if you have this type of software and you can compare it to your competitors, this is easy to market. But if you just say, okay, look, we can do something with you, we have the cool engine, but we have to develop things together. This actually takes much more time. And as a result, at least we experience, I don't know how it is with Nicola's group, right? That the interest is mainly from large companies, right? So it's mainly that they have, I don't know, innovation managers, and they contacted us, and we were just very happy and lucky or whatever. And then we have, of course, you talk to people, and then other people talk. So we don't really get our contracts through marketing. It's mainly through knowing people or getting requests actually from larger companies that want to use this technology. Okay, so this was a bit the public relations section of what ASP is. Now let's look a little bit at the history. And the reason why I wanted to put this up is just also to see a little bit how things flew together. But the other thing is also to realize that I think in knowledge representation, Boolean logic or classical logic has, of course, still a primary role. Even though for knowledge representation, and notably reasoning, if you want to model certain forms of reasoning, you need non-classical systems, right? But classical logic, of course, has a head start, right? Because, you know, with George Boole or even going beyond that, there is so many research in mathematics and in theoretical computer science was poured into that you can build things right away on very solid foundations, right? While in ASP, of course, and of course also the let's say the not ASP as such, but more or less the predecessors of ASP, you had to come up with mathematical constructions, and everybody had its own preferred mathematical construction. And that, of course, gave the whole field, let's say, a difficult time to be understood, right? But the cool thing is now I think everything is nicely distilled in the stable model semantics, which inside actually uses aspects from well-founded semantics. And I would like just to point this out or sketch this now in this next paragraph section here. Evolution of ASP. It's my view on it, and of course many people can see this differently. So I think one could have mentioned even the 50s, right, when John McCarthy came up with a frame problem, and they had to do, it was clear more or less that to solve this you needed non-monotonic formulas, and then the first ideas more or less were bounced around. But I think I start here in the 80s, where it was really about how can we see that there is this there are, let's say, implementations, algorithms, even logics for dealing with incomplete information. But how can we really capture it formally? And this more or less, I think, happened in the 80s, where Keith Clark actually formalized the closed word assumption for database and logic programming. I think this was the first really nice formal formalization of it. But again, different notions, right? Databases, closed word assumption. Databases are easy, just facts more or less, right? And then get, if something is not in a database, making it false is easier than in a logic programming fragment where it's about negation as failure. You can only say that something is, let's say, not provable if the proof finally fails. So if this guy runs forever, well, too bad. You will never be able to prove that its negation holds, right? Then non-logic reasoning there again. This I think was in retrospect the real design flaw in that was, I think, that people started to do it right away with first order logic. And this just got so complicated because, of course, first order logic is semi-decidable. Once you talk about non-derivability, it becomes undecidable. So you already had something that was pretty messy, and then you wanted to put things on top of it. And of course, you then had all these different ideas, autoepistemic, default logic, circumscription. And this was a whole zoo. But anyway, you see, there's different areas, and they had similar problems. And in logic programming reasoning, there was a whole zoo of different semantics, and people were arguing why their semantics better than the other and so on. But this was the first attempt to capture it because there was no historic mathematical foundation, as in classical Boolean logic, right? So people had to, this was a new thing, right? Aristotle didn't write about that, at least not that I know. Good, then in the 90s, actually people tried to amalgate and put it together. And the interesting thing is that actually the stable model semantics as such was developed from, actually the first definition of stable model semantics was done by Nicole Bidois and Christine Froidevaux, two researchers from Orsay in Paris, and they derived it from default logic. More at the same time, I think, if I remember correctly, their paper got first rejected, so I think it was done in parallel, but it appeared afterwards. Michael Gelfand and Vladimir Lifshitz developed it from order epistemic logic. And there is yet, at the very same time, a third definition of it from a philosopher. And Vladimir pointed this out to me recently, that in philosophy, they also made this definition at the time. So some of this was up in the air, and people just discovered it by themselves. But the interesting thing is that the logic programming semantics came from, actually more or less was influenced heavily from non-monotonic reasoning, but then offered as a semantics to logic programming. And I think the big step in that was also that more or less what people then did is, well, they said, let's look at the propositional case, right? And say, okay, let's assume if we have first order variables, then they only range about finite domains. We can instantiate the systematically, have a propositional format, and this will work in a much nicer. And then of a sudden, I think this was also a pragmatic boost to the whole thing. And somehow, I think people saw this just in the community of SAT, right? There was, for decades, first order theorem proving was really big and dominating. And then suddenly SAT popped up, propositional logic, and they were really successful. And I think this all, then coming back to the propositional case, taking the best of this whole zoo up there, then was one of the incentives actually why things just worked out that way. And well, basically then well-founded and stable model semantics were these semantics in logic programming. And interestingly, there is even a paper by V.S. Subramanian and I think Jack Minker and Chida Baral, but I'm not so sure. It comes at least from the Maryland people, that stable models can be understood as you do well-founded semantics as propagation, and when you can't propagate anymore with this well-founded operator, you branch, and in this way you get stable models. And this actually really is the nutshell. So every solver more or less aims at having a bit less or more or but it's the well-founded semantics that is used as the measure for propagation strengths, and you more or less need this in the end to decide whether a model is a stable model. And then once you propagated everything, then you branch, and this gives you the search tree with all the stable models. Okay, good. Then application and semantics. This was more or less in the beginning of this millennia, right? So first of all, we had more and more applications happening, but we saw this on the last slide. But then the real breakthrough here was on the semantic side. And I think we all have to be really thankful to David Pearce. Even though Dov Gabay, right, saw also this connection to intuitionistic logic before, but David Pearce really nailed it down, who said, okay, there's this logic that was studied in the 30s by Heiting, the logic of here and there, and equivalent to Gödel's logic G3. And this is the logical foundations of ASP. So you take these logics and then do a minimization step that gives you homogeneity, and this is the formal foundation. I think this was a big rediscovery that really boosted the field a lot, because suddenly you had a logical foundation of the whole thing, and you can more or less draw from the tiny logical foundations established at the beginning of the 30s. And I will actually explain this semantics briefly later on. And I think in the last decade was, I think, about customization, integration, something I think that happens in all paradigms, starting from first order theory, improving CP, SAT, that more or less you grow up, you become an adult, you want to be integrated in the real life. So you need APIs, application programming interfaces. You want to do more sophisticated solving, like multi-shot solving, where you do incremental stuff. Then you realize actually that, well, ASP will not solve all problems of the world, so you have to buy in, so you have to call in some friends, right? And so you want to have an ASP solver with constraint solving combined, or with I don't know, with different constraints or whatever, right? So you hybridize. That's what happened in SAT as well. SAT was there at the beginning, and then SNT was more or less eminent at some point, where you also want to call in theories, SAT modular theories, right? And we will actually talk later also, we will talk a lot about the APIs, we will talk about multi-shot solving and theory solving, and use actually constrained ASP as an example for that. So we'll be back. Good. So this was this little excursion on the history of ASP. Let's briefly look at the workflow. So again, the overall idea is you want to solve a problem, right? And you do that in the following way. You map it on a computer, and here actually you're not doing programming, you model the problem. So here actually you have a formal representation of the original problem. Unfortunately, for historic reasons, this guy is called a program, but it's not a program. We actually talk a lot about an encoding, right? It's just a formal representation of your problem. Importantly, this guy contains first order variables that range over a domain. Actually, in this case, just terms, right? And this is why there is this grounder box here. And a grounder does nothing else than take the logic program with first order variables, eliminate all of them in a systematic way, that at that point here, you get a propositional version of the logic program, and then the solver computes the models or does something with the models. You get the stable models here, then you read them off, and you get a solution. So that's the idea.
Sorry,
and
your speaker is not connected.
Yeah, that's my loudspeaker who wants to become Alexa. And what is, well, but perhaps before we go here, let me just perhaps erase the drawings. Just for those of you who are familiar with, for instance, with SAT, right? So in SAT, you don't have that part here. You directly have to go from your problem to the solver. And then this is something that you do yourself in C++, in Python, in Java, or whatever, right? And the encoding, the model, the representation of the problem then lies in the code of this programming language. And that's actually what you do not want to do in a knowledge representation and reasoning framework such as ASP, right? So again, just to make precise, this is how I view the approach in SAT. In CP, they also have a model, they also have modeling language, but I would argue that they are closer to better suited for computer scientists. And again, we can debate this, and I'm pretty sure that there are people who don't see it that way. And perhaps there's even software that does it differently, right? But at least I vouch for the ASP approach. Good. So let's root this. Let's actually see where this technology comes from. I think modeling definitely comes from knowledge representation and reasoning, even though the syntax is borrowed from logic programming. Then what happened in the grounder, the substitution of the variables in rules, is a technique that comes from deductive databases, right? And you can actually understand, even though we haven't seen what a rule is, each rule as an SQL query, right? And where you go into tables and you combine them, and then you project things out, and each of them can be seen as an SQL query. And the solver, as mentioned, right, most of the credit goes to SAT, or more or less the constraint driven constraint or clause learning, as the SAT guys say, right? And we will see come to that in a sec. we more or less took up this technology and adapted it to ASP. Then stable model semantics, again, it's more or less like Boolean models, just that they work under, the semantics works under closed word reasoning. And this is found in databases, non-monotonic reasoning, and logic programming, right? So this is more or less how the four mothers actually come into play when it comes to doing ASP. So usage of ASP. Well, I think what most of the people do, they use ASP as a high-level language. And there, it's important that you always actually write things in two components. You more or less you express the problem class as a set of rules, and this set of rules should work with all problem instances of this class. So then, in the specific problem instance, you represent as a set of facts. And then you push the button, do this workflow, and you read off the solutions from the stable models of the facts and the rules taken together. Okay, you can also use ASP as a low-level language in the sense, as we talked about it with SAT, right? That you take a problem and you compile it into a set of facts and rules. But this is really bad. And because what makes it bad is, again, that your modeling of the problem is now hidden in the compiler, right? And if you want to change it, or if you want to compare different alternatives, you always have to go back into the compiler to change things. The better approach, and that's actually what we advocate a lot, and that we also use in industrial applications, is that you compile your problem, but you compile it, you view it as a problem instance, and you compile your problem into a set of facts. And then the way how to solve this problem, just like above, and this is like an encoding for a problem class, you encode as a set of rules. Because then you have the encoding of the problem in ASP, you can read it, you can nicely manipulate it. It's what we see later, elaboration tolerant. It's not buried in the code of a compiler. And that's actually a big advantage for maintenance, but also when using ASP systems. Then, of course, you solve things as above by just reading of the solutions. Well, the other third approach that we will see actually is that you use ASP together with other languages, right? And there, it's more or less you have an ASP solver as an object in the software environment. You query this guy, it gives you, or perhaps several solvers talk to each other, and there you use APIs that more or less solve continuously changing logic programs. That's more or less the third way, and you have it inside a software environment. Good. So this brings us actually to the end of the very first, let's say, public relations section. Now let's get a bit more formal. Again, we get more formal, but I will not really make things very formal. The idea is, my idea is rather to give you an idea how to capture the semantics of logic programs in the setting of ASP with the stable model semantics. And as I mentioned before, when things started, when things were invented, there was no logical foundation. So people more or less used classical logic and then did meta-mathematical constructions on top. And we will first look at the Reduct-Based characterization, but actually from a slightly different view. Then we will actually, I will briefly show you an example how you can actually axiomatize it, in the sense that what do you have to write down in Boolean logic so that you get the same stable models of a program? And we will actually, And then I also briefly want to show you how this new logical characterization, well, no, not new, the rediscovered logical characterization works, that goes back to work of Heiting and Gödel, and was, I think, it is rediscovered by David Pierce. Okay. So what is a stable model? And actually, you see there are quite a lot of things, and we will more or less look at these guys here at the beginning of the course. If you look at the other material that we have in the master course, we also look at these other guys here. And here, basically, these will be the formal characterizations that we look at. On the other hand, there is a very interesting piece of work, as always, by Vladimir Lifshitz, a work which changes its titles, because I think now it has the title 13 definitions of a stable model, But I think this here were the 12 definition, that's the 13 definition, and who knows, I'm pretty sure that Vladimir can come up with even more, and perhaps he will. Okay, so in case you want to check this out, these are all formal definitions. Okay, let's look then at the Reduct-Based definition first, and I will present it rather differently, and in particular to make it easy for those of you who know just Boolean logic and want to know what is really the difference now, what's going on. Okay, first of all, some formalities. So we look, a logic program is a set of rules, and that's actually important. It's a set, right? Unlike Prolog, for instance, order doesn't matter. Permute your preferred Java or Python program, permute the lines there, and it will not be funny afterwards. But here the idea, when you permute, things will not change. Okay, then we have a rule, and the rule, if you like, is an implication here, where you have a head and a body of the rule. And the only reason why this implication is from right to left is because it was invented, I would argue, in a Western civilization, where you align your code on the left-hand side, and not in other culture on the right-hand side. So that's why it was switched around, because then rules with the same, that describe the same predicate, were aligned on the left. Okay, then otherwise we have atoms, right? So all these A, B's, and C's are atoms. And then here we have, this denotes implication, this is a conjunction, this is a negation. And the intuitive reading of such a rule is a head must be true if the body holds, right? But here this rule is actually taken really serious, in the sense that we will see logically after, this is a genuine connective, right? It's not like standard implication, right? That is equivalent to a disjunction. No, here you take this implication serious. You only accept derivations from facts of applying rules in a forward chaining way, and then you can derive things. No reasoning by cases, no reasoning by contraposition. This rule connective is particular. Okay, and then the semantics. What is the stable models of such a program? Is more or less a Boolean. Like a Boolean model, like a model that you all know, just that every atom that is true in this model must also be justified by a proof, actually a rule that derives it, and in this rule also its antecedents must be derivable until you go back to the facts. That's the really different part. And to spoil things a little bit, actually here you have actually two meanings of true even. And we will see that something is can be provably true or just true, right? Because it's a different thing if in the truth table it says, oh, we now check the case where this thing is true, and then you just check this case, or you also have a proof for it. And in ASP, actually, you have both. Okay, let's actually not spoil too much. Let's see a little how things go. Okay, so Reduct-based characterization, truth tabling. And again, when I write SAT, where's my mouse? Hello. Whoops. Oh, here we are. When I write SAT, I actually just let it stand for Boolean logic, the Boolean classical logic that you're all familiar with, just as to have a small buzzword, right? So, but we all actually know from our undergraduate days, whenever we are given here such a formula, how to evaluate it with truth table. So we have here the truth table. We have three variables, and here we have all 8 combinations, 2 to the power of 3, that they can take on, right? And now we want to find out which of these interpretations, which of the 8 interpretations is the model. So what we do is we more or less substitute. So we substitute B here, then there's the truth value for A here, C here, and you know a little bit how this works, right? Let me just briefly go through that. So we substitute the variables with the respective, so here we substitute false for all 3 of them. We see this here, right? And here the other combinations. And then we go on and evaluate, because we know we have the truth tables also for the connectors. Let's first evaluate the negative parts. So we get this. Then we look at what is not true or false. Here, these guys are false. So more or less, and is as a conjunction, the whole thing, we reduce it to false. Then these guys are true. We reduce them to true. Then we look at the conjunction. And what we get are among the 8 interpretations, 4 of them are models. These 3, and this guy, because they evaluate the formula to true. This is what we do in the classical setting. Now let's actually see a little bit adapting this truth table method to ASP. What is happening here? So, before I forget, I often actually abbreviate these models here just by sets, right? So this set here represents which one? This one, because here A is true and F and C are false, so I only include the true atoms, right? And the same for the other guys. And okay, I think that should be pretty clear. Okay, now back on track. Now that's what we do inside. Now let's do the same thing, or let's use the same type of truth tabling in ASP. Actually, what you do here is you say, oh, okay, actually somehow you don't trust what here the oracles, because one thing you can say is this: whenever you have here an interpretation, it's like an oracle, right? It says, oh, let's just assume this is the case and check it afterwards. But here you also want to make sure that when something is true, it is justified, it is supported by a proof. Okay, hence the idea is you only substitute the negative. Whenever you have a negation, everything behind the negation you treat as in classical logic. And so only those guys you substitute. So you substitute here the B, but for instance, A is not preceded by a negation. And again, this only works now for normal logic programs. So you need another definition for general formulas. And this guy you leave untouched, this guy and this guy, because it's not preceded by a negation. Okay. Okay, so let's just do that, right? We do that, we evaluate, and we get something that is then called a reduct. And now, by evaluating the negative part with respect to the interpretation, now we want to make sure actually that what the interpretation claimed to be true is actually true. And for this, we look at the reduct and see what can we now prove from the reduct. And let's see here, we have these 4 models, because stable models are among the classical models. They're just a restriction of the classical models to those where everything that is true is also provable. So we only have to look at those 4 here. So, and we look what can we prove here, and well, what has happened? So here actually, if we just have B and C in terms of atoms, right? Because here we claim that B and C is true, but well, we can't prove any of the atoms. So here we have actually A as a fact in the reduct, so we can actually prove it because it's a fact. But we cannot apply this rule because we don't get B. And the same thing actually happens here. So we can only prove A, and here nothing is provable. So if we now compare with what the interpretations were promising at the beginning, here this guy said, oh, A is true. And here actually is a proof for that, simply because in the reduct, there's a fact. While all the others more or less are a bit shaky in the sense that they say that something is true, but after all, it's not provably true. Okay, again, all in the ASP disguise that whenever you make something true, it should also be provably true. And here, after all, among the 4 Boolean interpretations, only one, and this is actually this guy, here it happens that you more or less, it claims that A is true, and actually there's also a proof for it. All the others that fails, and that actually is why also for the other interpretations, why this is the only stable model in this example. Normally you can have, just like in normal models, none, one, or several stable models, right? But here in our example, that's the only stable model because it's stable under rule application, right? So if you take the model and then you see what rules apply after you reduce them, you can reproduce the model because everything that is in the model also then has a proof. And that's why it's actually called stable. And so we get here in this case, a single stable model, which contains A. So, and yeah, what one view to see that intuitively is that the stable models are the smallest models of the respective reducts. And let's just briefly make this precise, right? Again, this is the original definition by Michael Gelfand and Vladimir Lifshitz. Again, we look at rules of this form. I just do this because when I use the R, I always want such a rule at my fingertips. So we can then define a reduct, and the reduct is exactly what we do with the truth tabling, right? We look at all the rules, and we evaluate the negative part. So here we look at all the rules, we evaluate the negative part. So in case none of the negative atoms is contained in X, good, then we add this here to our reduct. This way, this gives us here, this is then the definition of the reduct. And then we look at everything that is provable from the reduct, and actually everything that is provable, since this is a positive or even a definite program here, it corresponds to the smallest model of this positive program. This is given with this operator, the consequences of this positive program, right? And with these two things, we can then say, what is a stable model? Well, if you give me an X, and again, this is, if you have the true stable, this here is the X, right? If you give me the X, it's a stable model if after evaluating the negative part, everything that you can prove from it is exactly the X. This means there's not more that you can prove or less. You can exactly reproduce all the true elements in the model. And hence every element in the model that is true also has a proof, because it went through this procedure of removing the negative part, because this is treated classically, and then seeing what can you actually prove from that. Let me see, is there a chat message? Oh, Jacques, you raised your hand.
Yes, the negation, the literals here, they are negation as failure. Or classical.
Well, the thing is, here in this case, well, it depends. This is negation in this logical apparatus, right? And of course, this does not behave as classical negation, and people call it default negation or whatever, right? But as such, this is just a syntactic symbol that is treated that way. Right? So you can intuitively look at it as negation as failure.
Okay.
Well, thanks for the question, Jacques. Merci. Good. But the interesting thing is, and I think everybody, me included, right? I always looked, when I looked at this, actually at the negation. But we will see actually later on that logically, negation is irrelevant. The real, from a logic perspective, and again, we will see this later on, the real important connective is actually implication. Because the idea is that with this implication, you look what you can prove, and what you cannot prove will then be set to false. That's how then closed world reasoning will work. So it's interesting. That was also because I was also, you know, I was raised on Prolog, right? And also looked at negation as failure and stuff like this. And I was very surprised when then seeing the logic that it's about the implication, and that negation actually is secondary. But we'll come to that. Good. So then, okay. Now, those of you familiar with classic logic may say, okay, now this is it's a fixed point definition, and how does it really work? Can you express it declaratively in a Boolean logic? And yes, you can. Let me do this by example. Okay, now this is a logic program, and it's already a bit more complicated, but we have these 1, 2, 3, 4, 5 rules. And now, if we want to express this in Boolean logic, I think the first thing we can do is we can just interpret these implications as implications, right? Okay, and so that's, but the only thing I did now is, whoops, where's my, the only thing I did, look, there are two rules with X in the head. I put them here together, right? So this body here became this conjunction, and this body here became the Y here. But now actually what I have is a form where I have implications where each atom has a single, each of these rules has a single atom as a head. And this is needed because we will later perform a syntactic operation where we need this format. But now what we can always, what we can see now is this is now the rule formula. So you take the program, let's say this is a program here, and now let's say this would be the formula or the theory that represents this formula. And we see here that this has quite a lot of models, right? And in particular, it has models where, I don't know, let's say where C is true. And from an ASP perspective, this is very strange because look, there is no rule with C. There's a rule that could give us A, B, X, and Y, but there's no rule that could give us C. So all these models already that contain C are spurious. So then the idea actually of Keith-Clark in 78 was to say, okay, to explain actually negation as failure, and to explain also closed-world reasoning in databases. Let's just say that an implication actually represents both a necessary and a sufficient condition. And the idea was then to say, okay, we take these guys, but we add the other the other direction as well. So you see now we went here we now have here an equivalence. And so more or less all these implications we add this equivalence. But we do this not for all rules, but we do this for all atoms, right? And there's actually yet another atom C, and we have to say, okay, this atom has no definition, no rule, so this is equivalent to false. And this is actually what Clark's completion does. And again, our models were reduced, because now these are still the models of the formula that we had before, of the rule formulas. If we now add the completion formula, right? Or if you take the completion formula instead, which actually you can view it. So I wanted to have things on the slide in a compact way. That's actually why I replaced the implication by an equivalence. But what is happening is you have the implications in one direction, and with class completion, you add the implication in the other direction. You can view it like this. And then you destroy a lot of models. So all models, for instance, where we had C before, also a model here where we have B and A together, which can't be the case, right? Because you see they're disjoint. This is eliminated, and you only get 3 models. And that's already pretty good. But there's still one model, this guy here, which is not a stable model. And why? Let's look at this. So actually what this model is, it's a more or less, I always say it's a clone of another model. We have this model and we have this model. And if we look a little bit, so once actually B is, let's say in this model, actually B is true. Once B is true, you see that there is a loop, a positive recursion between X and Y. And now what this formula is too weak to actually say, oh, X is equivalent to Y, and there are 2 models, one where both are false and one where both are true. And that's what we get here, right? Here both are true, and here both are false. But of course, what you want, you only accept models where there is a finite proof for something, and you have to eliminate this loop. And actually, Fang Lin and his student Zhao actually invented at the time the loop formula. This allowed us really to axiomatize things. And what this loop formula just says is, well, you look at all these, the strongly connected components, all the positive recursion, and if one of the guys is true, that is, if on this loop X or Y is true, then it must be supported externally. So you see, these rules are circular, so you can't look at them. But here's a rule that would give an external support. You can derive X with atoms that have no X and no Y in it. And this would be an external support. So what this loop formula says, oh, if one of the elements in this loop is true, then an external support must make it true. It can't come from the cycle, it must come externally. And this is actually what happens here. So we have here this loop, but here there is an external support for one element in this loop. And the loop formula then says, oh, if one of the elements in the loop is true, then an external support must be true, and there's one. So this is okay. And this is it. Now, if we add this formula, this will actually, adding this formula will eliminate this here. And this is what happens. Now, if we add this, we only get the stable model. And this is now, by example, an axiomatization of stable models as a propositional formula in Boolean or classical logic. One thing already to point to is, look, and I think I have this on a slide to come, but this operation here is polynomial, more or less linear, right? This operation here is exponential, because you may have exponentially many loops in your program, and the loop formulas, hence you may have to add an exponential number of loop formulas to forbid all possible circles and circular derivations. So this actually is more or less the intuition between a result we will see later on, that if you actually compile ASP into a Boolean logic, into set, you risk an exponential blowup unless you extend the language. And again, those of you familiar with citing translations know that you can always somehow, if you add auxiliary atoms, then you can get away with this and have a polynomial translation. But again, if you do the translation on the same language, you may have you have an issue here. Okay, good. So this was the axiomatization by example. And here's the theorem. And again, perhaps you look at this later on. Right? I don't want to go through this. I was just more or less anticipating already what I was saying here, but I think it was better to see with the example. Good. So just to wrap this up, right? Actually, here are the two correspondences. So if you have an ASP system and you want to encode a SAT in it, the only thing you have to do is you have to add for all the atoms the law of the excluded middle, which is A or not A for all of the atoms. Then you have a SAT system, right? This is what you have to do. And actually in the system, this amounts to a choice rule. So whenever you write such an excluded middle, it amounts to a choice. And this is written in an ASP system like this. So I write the dot here, right? That's a choice rule. That's also written down here. But that's pretty easy, right? So if you want to compute all the Boolean models, you add all the choices for the elements in your vocabulary, or only for those that you wanted to, and that's how you get it. The other way is more complex, because here you saw that if we have a SAT solver, a Boolean logic, then in order to characterize the ASP models, we have to add the completion and the loop formulas to it. And again, over the same language, you risk an exponential blow up due to the loop formulas. Also, one thing we shouldn't forget, I was always talking about normal rules, about normal logic programs. But if you take Boolean formulas, arbitrarily nested formulas, then actually the decision problem in ASP is higher. It goes to the second level of the polynomial hierarchy. If you just do normal logic programs, as we've seen so far, you have an NP problem that just like in SAT, and that's actually why all these compilation things here make sense, right? Because you compile from one NP to another NP problem. But on the general formulas, you go to the next level. This just as a remark. Jacques, yes, please.
Yeah. So when you add the law of excluded middle, are you in effect reopening the world? Like, are you moving back to open world assumption?
Yes. It's once you add the laws of excluded middle for all of them, you have a classical. You look at the classical models. You're back to open world reasoning. Okay, I trust I answered your question.
You did. Thanks.
Thank you. Okay, good. Then last but not least, and this is, let me again, this will be hand waving now because I don't want to spend too much, but I just want to give you a little bit the flavor of the logical foundations. So let me perhaps, when we deal with classical logic, let me just do this. Okay. When we do Boolean, let's say Boolean or classical / classical logic, we have one world. And this world is, when we have our truth table here, we have all the worlds, the states here, right? Actually, in an intuitionistic logic, we have Kripke structures. We have actually structures, arbitrary structures, where we look from one world in another world. And the only thing what is important in an intuitionistic logic is that all the propositions that are true here must also be true here. So whenever you go from one world to the other, truth persists, and only things can become, other things may become true, but you never lose truth. And this actually makes the implication constructive. Okay. Now, what we now look at in our setting, it's actually sufficient to look at two models, here and there. That's the here world, and that's the there world. And this is an intermediate logic, something that is between intuitionistic and Boolean logic, but you have this. You can look at this as a hierarchy of complexity. Let's say it's the strongest or logic that you get before you get to classical logic. And that's this logic of here and there. And that's actually enough. You can also have more complex worlds if they would do the trick, but David Pierce showed that having these two worlds is enough. So let's look at this. So again, we've distilled things down now from Kripke structures just to sets of models. So an interpretation is a pair. And this can be, again, for those of you who know it, it's a Kripke structure with two worlds. The first one is called here. The second one is called there. And there is this condition that the implication actually is constructed, that everything that is true here is also true there. So you can look from the here world and the there world, and of course they are reflexive. they are reflexive. So this is called a crypt-key, a very simple crypt-key structure. So the intuition is that everything that is true here is true and provably true actually, and everything that is true there. And again, we talk now about this is the here world and this is the there world, but I just use this now to illustrate how they are related, right? And so this means here everything that in the here world is provably true, everything in the there world is possibly true. So it can be true, it behaves more or less classically, but it's not yet that you don't have a proof for it necessarily. And you also have all the probabilities, and everything that is out here, right, is false. And this actually gives you also a type of a three-valued setting, right? So where you have provably true, these guys, everything that is false is out here, and everything that is in between the false and the here world, that is this, everything that is true here is possibly true, undefined. And that's actually why this corresponds to Gödel's logic G3. For those of you who know about these buzzwords, okay. Good, so just, again, I'm hand waving here. This is, if you really want to read about, David Pierce has great papers about that. So again, if something is then entailed in this logic, it means it's provably true. And if something is actually true just at the T world, it is possibly true. It is classically true. That's actually where classical logic, because you just have one word at your fingertips. And then if you look at the at the satisfaction relation, you see actually that implication is used like a modal operator. Implication, actually, there you change the world. Whenever you have a Boolean, a monotonic operator, you don't change the world. You just check in the same configuration. But once actually you look at an implication, you check actually that something is true in all reachable worlds. And here there are only two, so it must be true here and it must be true there. That is the proof that you found here must also be available in the there world. And what you see here is it's really implication, the correct. It's not really negation, because after all, negation is simply defined in terms of implication. You don't really care that much about it, at least from a logical perspective, right? But it actually, a little transformation just shows that something is, a negated formula is true if it is not entailed by the there world. And this is more or less, again, for those who know intrinsic logic, is when you have a negation, things behind the negation behave classically, and that's also happening here. Okay, again, just hand waving. Okay, and of course, interpretation of the model, if it is entailed. And now this is all monotonic still, right? So we have not done any fancy. The only thing we did is we have weakened our logic. We can prove less tautologies in this logic than in classical logic. For instance, A or not A is not true. But now we know at least that these things that are true are provably true. And now the idea is to make a construction on top, a minimization, that everything that is false, everything is undefined, that is not provable, will be set to false. And this is happening with this equilibrium construction. Oh, shit. Let's just skip that, because you can just read this up later on. It just shows that all classical tautologies are true. This is this equilibrium construction of David Pierce, where the idea is more or less that you now look at the total models, and you want to make sure that the model that you have, it's a model of a formula. It is a model. And then also you want to make sure that it's minimal, in the sense that you cannot find another model. Actually, I forgot to say here that HT must also be a model. Actually, Roland told me, I just forgot to do it. There cannot be another model of the formula, right? No, shit, forget about it. I hope that my swear word will be edited out later on. Anyway, you cannot find for the same T a smaller H that is also a model. Right. Okay, good. And if you have such a guy where you choose things to be as small as possible, it's total, right? And then you just take this total thing, and this is actually called, this is a stable model. And this is more or less how the non-homogeneity comes in. And again, just to wrap up, and this acts like a classical model, has all the properties, and there's actually a nice relation to the reduct, right? So whenever you have such a guy, and it entails a program or a formula, it's the same thing as if the here world satisfies the program reduced with the there world. And these are all the corresponding. Again, this is just hand waving. I don't expect you to understand that, but perhaps you got a glimpse, and perhaps it interests you and you read up on things, right? That's more or less the intention, because I find this important that this rediscovery in the 90s then has such, I think it's beautiful, right? So, and it gives us a lot of formal power to elaborate extensions of ASP. So for instance, we work on extensions of ASP with linear temporal logic and with linear dynamic logic, and just taking this logical framework helps us so much to fix the semantics right away and work from there without doing any meta mathematical construction. Because imagine you want to define an extension of ASP with linear temporal or linear or whatever logic, and you have to do this with a reduct or with meta mathematics. It's really much more complicated. But in such logical setting, works like a charm. Okay, good. So now back to very basic stuff. Let's briefly look at grounding. And keep in mind, in a workflow, we have a program with variables, and grounding is more or less the process that systematically eliminates all these variables by ground terms. Yes. And that was, and again, I will not go into details, more or less just hand wave a little bit here. Ground instance, what is this, by the way? Okay, so we have a set of terms, we have a set of atoms, and first of all, they may contain variables or not, but in the end, we are interested in variable-free ones. Those who are, and this can be, I don't know, here are just examples, right? So this is a numerical constant, a string. This is a variable because it starts with an uppercase, and at least that's the convention normally that you have, right? And then you can compose things with function symbol, and you have arithmetics. And then, of course, in the same way, you have atoms, and there can be function symbols inside, and you can actually remove these guys. And I think it's pretty fun. This is more or less a language, and many of you may know that one is called the Herbert universe, the other is the Herbert base. And this is the basic of also the interpretations. We just refer to this as an alphabet. Okay, now just to fix what a ground instantiation is, right? First of all, a variable-free atom or term is called ground. So whenever I talk about ground term or ground atom, there are no variables in it anymore. Just ground terms in an atom. Good. So that's good that this is then a ground instantiation of a rule. So you take one rule with first order variables, and then you obtain a set of ground rules from it. And what you more or less do is you take the variables in the rule, and you take a substitution that maps them to some terms. And you more or less look at all the substitutions that take these variables and map them to terms, such that when you apply the substitution, there are no variables left. So everything has been replaced. And so and then you collect all the ground instances that you get, and this gives you the ground instantiation. So you systematically replace all the variables by ground terms, and then you get a big bag of ground rules for a single rule. And then you do the same thing for the whole rules in the program, and that's then what we get here. That's a ground instantiation. And you can imagine, first of all, that this is easily infinite, right? Because once you have a function symbol or so, right, you make it infinite, infinitely many terms and so on. And this is somehow not a problem to have an infinite language. You just have to make sure when you write an encoding that you encoded it that way that there is a finite representation of it, and the grounder can find it. That's of course something that comes with modeling. And one should not forget, I was nicely talking about ASP is at the second level of the polynomial hierarchy and so on. But this is the solving part. The grounder actually, which is just to mention, is Turing complete. You can encode actually a Turing machine, and the grounder can just execute it, right? So it's a bit strange, right, that this pre-processing part is much more powerful than actually the real solving. But well, in this way, you want to support a nice modeling language, well, you have to make it expressive enough. Okay, now let's actually see how things work here a little bit. Jacques, yes, please.
Yes, so it means that we can have an ASP program that has function symbols and with recursive rules?
Yes. Oh. Yes. You just have to make sure that your recursion somehow behaves well, that the grounder can terminates and gives you then a finite program out of it.
Okay, so there are some syntactic restrictions for the grounder.
Well, you know, there's a simple one. If you have something like, I don't know, you have a P of 0, and then you have, I don't know, P of x plus 1 if P of x. You got it? Mm-hmm. Then this is infinite, right? But if you then add that x must be smaller than 100, You have
Okay.
limited that.
Okay.
So, and this is a simple trick, and with terms, you have to come up with something similar. But later on, I will be talking actually about incremental solving. And with incremental solving, you can more or less enumerate the thing. You can also then really go into the infinite, but you just have to have then a parameter that you increase, and that then you can recursively enumerate things if you want to.
Okay.
Good. So grounding. Oops, I was now too fast. Where am I? Here we are. Good. So here's a very simple program, right? So we have two facts. This fact. I just write this pedantically now, still with the rule. And here's the rule. And this rule does nothing else, right? Whenever you have a pair holds for the relation R, you also get it for T, right? Nothing big happening. But keep in mind, when we now instantiate, we can take advantage of the stable model semantics, of closed world reasoning. For instance, the simple thing is, whenever there is no rule that allows you to derive an atom, this atom can never be true in a stable model. It can never be provably true. So you can take this information and then continue with cascading simplification. And that's a little bit how things happen here. So if we have this program, we have three terms, A, B, C, and we have, I think, 18 atoms. And more or less, our interpretations now are in principle over these 18. So we have 2 to the power of 18 interpretations, theoretically, right? But this is very simple, and the grounder sees actually this. Let's see how this works. Now, this is the ground instantiation, right? So we have, these are the two facts we had in the input. And now we got for X and Y here, in principle, by just saying, okay, here I can replace, here I can put A, here I can put A, then I can put A here and B here, and of course this then continues, A, B, and I get all the combination, and these are all the combinations we have, right? So we have 3, 6, 9 different rules. Let me just erase that again because it's a bit sloppy. Okay, but if you then look at this a bit closer, right, you actually see that, for instance, here we have R of AA. Now, is there a rule that allows us to derive R of AA? And no, there isn't. Actually, you can just derive R of AB and R of BC. You can't derive it. So you can actually, this guy will be false. So this rule will never apply. You can even remove the rule. Okay, so what if you do that? You can more or less replace all rules that have positive body literals that can never be derived. We eliminated actually 7 now, and now these are left. And here actually you can also do a simplification, because since you can see that this is a fact, this is unconditionally true, it must be true, then this guy can be true as well. You can remove this, and you can also remove this one because they are true. In the same way as you just removed before many because the atoms were false, now you can also cascade things because things are true. And you actually, the grounder can evaluate this and just say, oh, this is equivalent to these 4 facts. So these rules here give you atoms that must be true and all the rest must be false. So grounding actually takes the stable model semantic, this closed world reasoning into account to simplify your output as much as it can. But this is just your strategy's heuristics. In the worst case, it will overflow, and of course this has also a lot of sources of combinatorics, because after all the instances, this is a very simple rule, right? But by instancing each rule, you actually solve a constraint satisfaction problem, right? You have to take elements from domains, and there may be constraints like, I don't know, X plus Y smaller than 7 or something else, and instancing each rule is more or less a constraint satisfaction problem. Good, stable models. Now, what does those stable models mean if I have first order? Well, that's actually pretty easy in the way that you take the program, you ground it, and then you apply the definition of a stable model to the ground program. And of course, this only works if this guy is finite and there's a finite set. But there are also infinitary semantics and stuff like this, again, well beyond what we do now. But that's, in this way, you just lift it by saying, oh, I just look at the grounding of it. Instead of looking here at P, I just look at the ground program. So you're back to what we've been doing before. Okay, now this was ground instantiation and stable model semantics. Let's now see a little bit how grounding works. And actually, since grounding relies on deductive database techniques, we also need some restrictions on where do we get the bindings from. And the idea is is a bit intuitively like the following. It's like if you evaluate a database query, right? You have to have tables at the beginning. And these tables give you, well, firm information. And then you can evaluate a query by inserting these tables. And then you can evaluate this query. And then when you derive something, you can then get to the next query where this appears. But you start more or less from the tables and you move up. And that's actually the same idea here. And that's actually why programs have to be safe. And I think it's also called in the database literature range restricted or so, where it's more or less this, where do you get the instantiations from? So we have these safe rules. And this is also when you use Klingo, for instance, or DLV, that rules have to be safe. It means that all variables that occur in the rule, no matter where, have to occur in a positive body literal. Let's just do some checks. So, so the first rule, well, there's no variable, this is trivially safe. So second rule, well, there is a variable, but the variable x does not occur in a positive body literal, so this is not safe, it's unsafe, you can't write that if you want to write a safe program. So the third thing, oh yeah, there is a variable x, but it occurs in a positive body literal, namely this guy, that's good, so that's safe. Next one is unsafe because it occurs, so the only variable x occurs in a negative body literal, so isn't safe. And here the last rule is safe again, where there is of course a non-q of x, but you made it safe by adding more or less a predicate from where the instantiations can be taken. That's safe again. And then of course a program is safe if all rules are safe. And once you have safe programs, you can then do what is called semi-naive database evaluation. That's actually what modern grounders like Gringo, that underlies Klingo, and the grounder in DLV are doing. So let's just look at our program and sketch a little bit how things work. So the first thing actually that the grounder does, of course, it parses the program, and then it builds actually the graph of the strongly connected components from it. And then you get another graph where the nodes are the strongly connected components of the original graph. And the cool property of a graph consisting of strongly connected components is it's acyclic, and then you can totally order it. That's actually what a grounder does. And so after doing this dependency analysis, you get a topological ordering of subprograms here. And in our case, this is I just took it that way, right? So you have here everything about R, and then in the next partition you rely on. So these are all the rules that may actually rely on R on the first partition, and then give you new ones. And if there would be a third partition, it can rely on T and R. And you see a little bit how it goes, right? So that's the first thing, you partition thing, and then you just ground one partition after the other. So here in this case, well, that's pretty trivial, right? So you have these rules here unconditionally, and the grounder figures out that actually not only that these are possible atoms to derive, that they belong to your set of atoms, but also that they must be true. So the grounder even in this case finds this out. Then you ground so you've done that, and then you attack this guy, but with this information here in your backpack. So you know actually that only R of AB and BC are derivable and no other combinations. And accordingly, it will result only in rules that have atoms in the body that are possible due to information that you gathered on grounding the first component, right? And so this then results in these rules and these ground rules, and the atoms that were possible is more or less, it remains internal information to the grounder, and that's then the resulting ground program. And you see a little bit how it goes. And it's again, by more or less only allowing instantiation that rely on atoms that were possible in former components. This already accounts for this closed world reasoning, right? You can only only generate information that you know actually is at least derivable, possibly derivable. Okay, so this is how grounding works. Now, let's just briefly go through this. Oh, Jacques, yes, please.
Yeah, is this somehow related to stratification or not at all?
Well, stratification normally is a much stronger requirement. So the thing is, here you may actually also have programs that are not stratified. What this means is then that your components get larger.
Okay. Thanks.
But if you have a stratified program, actually the grounder can decide it normally.
Okay.
Good. So again, solving. Now we talk about grounding. Let's talk about solving. Again, not going too much into details because modeling is actually the thing that I just want to start after we had a little break, right? So again, as I mentioned, we rely on modern ASP solvers, and as Klingo or our solver rely on a technique that is called conflict-driven. I call it constraint learning because I think it works with constraints, but originally the SAT people coined it clause learning because they dealt with clauses. And then I will briefly talk about the engine. So again, hand waving. So we now talk about how do we compute the stable models. So the first thing to perhaps to mention that it's again what I was saying before. ASP is a part of the knowledge representation and reasoning communities, and also on the reasoning side there are other demands. So the first ASP solver, namely S models at Aalto University or at Helsinki, right, had already a lot of these features. So it's not only about satisfiability. You also want to enumerate. You also want to enumerate stable models. You want to project. You want to enumerate, but only on a subset of the alphabet. And here, actually, if you do this in a straight way, you run into exponential space because you do solution recording. But I would say that we were among the earliest, actually, who had dedicated algorithms that run in polynomial space simply because this was needed for knowledge representation and reasoning, right? You wanted that. Also, well, intersection and union, that's pretty straightforward, and optimizations. This is more or less, these are the basic reasoning modes, I think, of an ASP solver. And what you often want are combinations of it. So we have, I think, most prominently in bioinformatics application, right? You want to capture an organism, you have a lot of noise, so you get lots of stable models that characterize actually one organism or one data set, right? And then at least you would like to say what must be true, and this is the intersection of all stable models, and what is never true, which is the complement of the union. Then perhaps you don't want to look at the stable model, but at the optimum stable model, because you have an objective function that, I don't know, that maximizes sugar or maximum on the minimal heat or whatever, right? You want to combine all these guys, and this is actually something that you can do very nicely with ASP solvers. Okay, let's then come to this this solving technique. More or less a traditional backtracking technique due to Davis, Putnam, Logman, and Lovman consists of your unit propagation, right? And you do backtracking like we know it. And this was also built in the first ASP solver as models, as I said. So modern solvers that use this conflict-driven constraint and also do unit propagation. Nothing changes here. But they do not do backtracking. Rather, they do something more elaborate in the sense that when you hit a conflict, you don't just backtrack. No, you start to think. You look at the conflict, you analyze it, you modify it, and then once you modify it, you can read off actually where the conflict occurred. So you jump back to the origin of the conflict, you add actually this new information at that point, then you resume propagation more or less, and the whole procedure. And this is then called conflict-driven no-good learning. And let's just look at the algorithms perhaps side by side. So this is a DPLL style algorithm, and I presented it. Actually, Martin Gebser did that at the time in a way that we can see nicely the differences, right? So you have a loop, you propagate as much as you can. Well, if you have not obtained a conflict but assigned all variables, great. You return the solution, right? I'm now here. So no conflicts, all variables assigned, great, a solution. If not, if you have no conflicts but they are still undefined variables, well, you pick a variable, assign it a truth value, and continue. And otherwise, and this means otherwise now we have a conflict. If the conflict appeared without making any choices, no decisions, then the problem is unsatisfiable, you just return it. Otherwise, you do backtracking, right? You unassign the literals that are propagated after the last decision. You flip this decision and go in the other direction. If you've already been there, then you go to the next decision. That's what I think you all know backtracking, right? You go one level up, you flip. That's what backtracking is. And now CDCL, where you do back jumping, can then just be explained like this. So you see everything, actually everything here stays exactly the same. Just, oh, I'm so sorry. So everything, I want to say that everything here stays exactly the same, just the last two instructions. And here, let me just remove that again. Just here things change, where you don't just backtrack and flip. You first analyze your conflict, and you take the conflict and you back jump to where this conflict actually will give you a propagation again, right? And that's actually what this is. If you look at it like this, it's a small change, but a lot comes actually with it. But that's the basic idea. And this technique gives you several orders of magnitude over simple backtracking. Yeah. And so looking briefly at the engine. Well, I think before we really go into it, I think Benjamin Kaufman, who actually implemented Clasp, the solver in Klingo, said that 10% of his code is a SAT solver, or would give a SAT solver, right? And the rest is really ASP specific. You know, special handling of certain constraints like cardinality or weight constraints, reasoning modes. So you have this enumerator. But anyway, let's just look at the workflow. So what is happening is you read in the logic program, right? So we are now here. You read it in, and then the program builder more or less does pre-processing. There are two phases of pre-processing. The first one is that does logic programming pre-processing, and then it does and then actually the logic program is translated into no-goods. If you may want to, you can think of it as certain clauses, and then pre-processing that is adapted from SAT is actually then used to shorten this. And again, you have to adapt it. You cannot use this off the shelf for technical reasons. And then once you've done your pre-processing, you build your data structures, and actually. We have here in class, we have actually dedicated data structure for short no-goods of size 2 and no-goods of size 3. This was also done in early SAT solvers, for instance, but I think I haven't talked to Armin or Mate recently about that, but I don't remember that they still keep short no-goods. But here in ASP, it's really important because 80% of the no-goods, or the clauses, if you like, are short, size 2 or size 3. Okay, and you also have to keep the dependency graph, the relation between the atoms and the bodies, simply because for checking whether there are for singularity in the proofs, what we've seen before, right? Good, then more or less the solver in Clasp is multi-threaded. You can have up to 64 threads, but I wouldn't suggest that. That is more or less the general scheme, right? That you more or less you work in a conflict-driven way, right? You decide variables by decision heuristics. You assign them. Then you do propagation until you hit a fixed point. You may learn no goods. Then you do conflict resolution. And this is more or less a standard CDNL procedure, except that here we had right away from the beginning we had post propagators, because we implemented actually the check for that more or less implements the loop formulas, right? That there is no circularity in it as a post propagator. And in a way, you can view this architecture down here as an SMT solver, where the theory is something that implements ASP specific stuff. One way to look at it. But I think what also is different is, again, it's this enumerator, and actually a data structure that was invented or first used by the guys in Helsinki, which is more or less the guy who says to the solver what to do next. So if you want to enumerate, this guy says, oh, thanks for the model, please look for another one. Or if you optimize, right, thanks for the model, thanks for the bound, now look for a better one. And this is more or less the guy who implements the reasoning modes. Okay, now here I would suggest that we stop, because now we come to the next large part of the course, which is about modeling. And my suggestion would be, well, are 5 minutes enough for a pause? Or do I hear a lot of protest now? Okay, then let's do 5 minutes. That gives me enough time to have an espresso. And I see you back at 15:40. See you. So let's get going. So I will not go now through all of this, in particular the case studies, right? All of them, because the material is there. You can look at that, and I just want to point out certain things and then want to make sure that, let's say, look, we now have 40. I would like to stop here at 4 and then take the last hour actually to talk about the more advanced topics, in particular how to, or perhaps 10 past or so, right? So not to overspend on that, and then talk a little bit more about ASP engineering. Okay, anyway, this being said, first thing, elaboration tolerance. Again, something that is really deeply, I think, rooted in knowledge representation and reasoning, and goes back to John McCarthy, who said, well, what is a good knowledge representation language? And his argument was, it's one that when you do a small change, when there's a small change in the real world, it's reflected by a small change in your representation. And I think this is always a bit of a guiding principle also for us. And that's how logic programs are more or less designed. That whenever you have attack a problem, that you come up actually with a representation where things are modeled as facts, and then you write an encoding on the side. Okay, let's first look at the language constructs. Good. So, oops, I was too quick here, I'm sorry. So first of all, we've already seen that programs are composed of facts and rules, and they have in general this form here. You see that this guy here is the implication connective, this is the end, and this is, you terminate each rule with a dot. So you may write your ASP program on a single line, but you just have to put a dot among all the rules. And this is now a constant, and this x here is a variable, and now normally you give both to the grounder, and it will instantiate both to this form here. Okay, so this is more or less how the basic ASP construct looks like. A very useful thingy that is perhaps hard to grasp at the beginning is our conditional literals. These are these guys. And let me just write, so in case there would be an opening parenthesis and a closing parenthesis, I think you had no problem understanding, oh, this is a set. It's a set of all qx for which r of x holds, right? And that's exactly the idea. So what you do here, you accumulate, you collect all the instantiations, the replacements of x, so for which r of x holds, and then you collect these guys, but you do not leave a set here, because here in the body you have a conjunction. This will expand then to the conjunction. This will expand to the conjunction of all the literals. So if you do this actually at other positions, it will expand. It may expand to something else, but that's more or less the idea. And it gives you a very simple way of quantification, right? Or you want all the x's such as a certain property is true, and you can write it down like this without really knowing what is the case. Very useful in modeling. Okay, the other thing is disjunction in the head, right? This is just to mention that because I won't really do any problems with this, but here's disjunction. Disjunction is actually a connective that adds complexity. It gets you from the first to the second level. Then there are integrity constraints, and yeah, well, I think most people who look at ASP for the first time say, oh, why do I have to? I think this is useful. I want to express that there is no x for which q holds and p holds, right? Okay, but you have to define it in a negative way. And logically, of course, you know, we all come from logic. We all like it. This more is abbreviated. This actually, it gives you a contradiction. That's actually why there is no head, because this stands for a contradiction. Let me just erase that. And people have to get their head a bit around doing that. We will actually see this when encoding SAT, because you have to encode things in a negative way, which, well, you have to get used to. But this is the way it is, and it has some logical motivation behind it. Then what is also often very useful for modeling are choices, where the idea is, well, you fix your y here, right? Let's say you write a 7, and then this is replaced by 7. And then you accumulate, this is now a set, right? You accumulate all instances of px7 for which, so that for x, q is true. This gives you a set of instances of p, and then you have to pick at least 2 of them and at most 7 of them. And this gives you a derivation, just with concept. Oh, okay, here's your bucket of instances of p, and you have to draw at least 2 and at most 7, but no matter which one. And that's, look at configuration, right? You have sets of hard disks, you want to pick some, or even the sum or stuff like this. Okay, I'm bubbling. So choice rules. Then of course the same thing works also for more sophisticated aggregates, where you can say this is a count here, this is now a sum, and here you have a term, and this term is extracted from an instantiation somewhere here, right? And this is again this conditional, and here you want that at least the sum is at least 2, and again at most 7. This is more or less the core these are the core constructs in ASP languages. And then you also have optimization, and one way, and you have two constructs actually in ASP, simply because one was put forward by the Calabria school, the other by the Helsinki school, and this we just took both of them because they are useful. Anyway, the idea is more or less you write things in the weak constraints. As weak constraints, you write things down as like an integrity constraint, that here instead of a minus you write a tilde, and this says, oh, you can violate this constraint, but if you violate, you pay a price. And this is, in this case, actually here C is the price. That's the first argument in this here. And here you can do actually a multi-objective. So it's a lexicographically ordered optimization. You can have levels for the objectives. That's one thing. And the same thing can be also expressed as a minimized statement, which is this form, which was first put forward by the people in Helsinki. So anyway, both do the same thing. It's just a different syntactic way of writing things. So now we are equipped with the language constructs. Let's now look at modeling things. Okay, and again, let me jump perhaps a bit over certain things. This is again the elaboration tolerance, and I think we talked about that, and also how that we want a uniform problem representation. So the idea is always that if you want to encode a problem, you have two parts. You have an encoding that encodes the problem class, and this encoding should work for all the problem instances. And with the instances, you more or less fix the format, and then everything has to work that way. It's really bad practice if you generate rules, for instance, right? It's really, if you have your problem, put everything into facts, write an encoding that then interprets these facts. And we will see metaprogramming later on, where we use this actually to write our own ASP solver just in ASP. Very cool, very cute. Okay, good. That's that idea. Then again, look at the ASP solving process briefly, right? We have a problem. We represent this problem in a formal way in terms of a logic program. This logic program is then grounded. There's all variables, object variables are systematically replaced. We get a propositional program. We give this to the solver. It computes stable models or operates on stable models. And I think one particular thing about ASP is that it's very easy now to, if you have a bug, if your stable model doesn't look like, right, it's very easy to just go back and elaborate that, right? Because after all, you have symbols in the language, and and you can elaborate with these symbols. You find whatever you get here in your stable model, you have the same symbols here in your specification. You don't have to go into a program that generated Dimax format or form like in SAT or so on, right? This is really very close, and this loop is hence very tight. And I think this is also an advantage of ASP, that you work with symbols and that you have them at your fingertips and not somewhere else and have to re-extract them again. Okay, that's the ASP workflow. Now let's look at a problem and model it that way. The problem we are looking at is just graph coloring, right? So first thing we have to think about is, how do we divide things up into problem instances and problem encoding? So here, this is easy. Problem instance is a graph consisting of nodes and edges. Okay. Now we have to think of how to represent that. And well, I think the obvious representation is you have two predicates. This is a graph. You have two predicates, a unary predicate that is a predicate with one argument for the nodes, and the predicate edge, which is binary for the edges. And here actually it's a directed graph, but it's yes. So, and here perhaps this is obvious, but in many cases, actually, when you start modeling, at some point you want to perhaps even to revise the fact format because you just want to put things differently. But we will not come to that point here in the course. Then the other thing that you need to represent as well is, or at least think about it, initially is you want to color it. You also have to have something that represents the color, right? So you also need a predicate for the color, depending on how many colors you have. Okay, that's more or less the instant format. Now let's look at the problem class. Well, here's the formalization. So assign each node one color, such that two nodes connected by an edge have the same color. Very succinct, very much to the point. But now for modeling this, well, you have to extract the bits and pieces. And what is better is actually if you decompose this in two constraints. In this case, again, this is my personal opinion, and perhaps other people may see that differently. So I have one constraint that says, oh, each node has one color, not 0, not 2, exactly 1. And whenever I have an edge and there are two edges that have been colored, that it cannot be the same color. And this is, I think, an equivalent representation of the first, but it's more, it's a bit better to have the constraints actually worked out. And don't underestimate this phase, right? So this all looks like trivial and obvious, but if you really have a problem that you want to model, this is really an important phase that you clear your thoughts. And many people have problems with that, right? So actually when we go out and to customers with a company or even with fellow academics, getting them first of all to formulate the problem precisely is a major thing, and one should not underestimate that. Good, okay, I zip it now. So now we have put down, we have more or less put the problem right. Now let's actually model this as a logic program. So here is now our graph from the beginning. We have six nodes. This is actually authentic code. There is this dot with which you can define ranges, which is most dot 1, 2, 3, and 6. Then we have these edges, and we have 3 colors. And this then represents our problem instance. And normally this guy goes in a separated fact because you want to color several graphs presumably, right? Not just one. And now let's come to the problem encoding. And again, we had these 2 constraints. You don't want each node should be assigned exactly one color, and whenever you have 2 nodes colored, they cannot have be colored with the same color. So here we have, now this is we use a cardinality constraint that I now wrote slightly different just to show it to you. Instead of writing here a 1 left as a lower bound and a 1 as an upper bound, you could directly write equal 1. So this means whenever you pick here a node, and let's pick a node, right? Let's pick node 3, right? Then you have instantiated n, so there's also a 3. Then we talk about assigning colors to node 3, and here we have 3 colors. So we will have to there will be one instance with 3 color with red, 1 with blue, and 1 with green. So we will have 3 ground atoms in this set afterwards, expressing that 3 can be colored with red, blue, or green, but we must pick exactly 1. Okay. Now, if we just take this encoding, throw it to the ASP system, we'll get a lot of colorings. For instance, also the colorings where everything is painted in red or in blue. So we have now to add the second constraint that says whenever you have 2 nodes, they must not be colored with the same color. This constraint. It's an integrity constraint. It says, well, whenever you have an edge with 2 nodes and an M, it must not be the case that they have been assigned the same color. And that's it, folks. That's more or less how you express this in ASP. And actually, we can learn already a little bit from that. The first thing is, this is now the problem encoding. But this is actually very representative for many encodings that there's actually you can actually view this here as a generator that generates potential solution candidates, and this here as a tester. And a bit like in complexity theory, right? Where if you have an NP problem, someone gives you a solution and you can verify it in polynomial time, right? That's also a bit here that you have this generate and test methodology for specifying problems. They're not solved like this by a system, right? It's just for writing them down. What is the best methodology? Okay, and that's it. So if we put them now in 2 files, a graph LP and color LP, one for the instance and one for the encoding, we can now ground them. And so I now use Gringo, and I use and this is the ground actually that underlies Klingo, and this is now the minus text option. You can do the same thing right away actually with Klingo. I'll show you just in a sec. So, and then we get actually this is the problem instance. This is now expanded. So for instance, here that you've seen that where's my mouse? That this node thing, which was before a 1 to 6, has now been expanded, right? That's what we have here. And then this has been given just like it is. And then we have instantiate the non-deterministic choice. So before we talked about 3 coloring 3 with red, blue, or green, and we can only pick one of them, and that's the same for all the others. And then we have even more integrity constraints. Again, let's just look at the first. This is for the edge between 1 and 2. That's actually for this edge here. So the nodes on both edges cannot be colored both with red, both with blue, and both with green. And that's, of course, then for all the edges like this, and you can see that here actually omitted some guys, right? But this is what comes out on the ground, and you already see, oh, very cool ASP encoding to begin with, two constraints, right? But now, well, but that's the way it is. This is not ASP's fault. That's more or less whenever you start with the first order representation, you ground it. This happens. That's the same in planning, in SAT as well. But here the cool thing is you have a grounder, something which is standardized, which is off the shelf, which does the job for you. Okay, then again, as I said, what you should look at is now Gringo. The same thing, the same command you can do with Klingo, and it calls underneath Gringo. So that's the same thingy. Now let's look at this. Let's invoke the solver. So here I just spelled it out. So you take more or less the grounding. Now I did not choose the text option because I wanted to be machine readable. I pipe this into the solver, and with the 0, I indicate that I want all stable models. And this is what I get. That's again a bit of an old version of class, but the result is still the same, right? You then get 6 answers, and these are all the possible colorings. Again, I omitted some stuff here, but these are now the assignments that you get. Let's pick one. Oh, of course, everything that you do here with launching Gringo and class can be done just by one call, Klingo. Same thing again, you launch it automatically calls the solver. You want all solutions. Good. Then looking at the stable models, again, just picking one, I put 6, you interpret this. This will be the solution, and you're back to you have your solution. That's more or less the workflow. Okay, now methodology, I think we already talked about this generating test. Let me be very brief on that now. Just look again at our example here, right? So we have the problem instance and problem encoding, and normally you structure, when you write down your encoding, you structure it in a way that you start more or less, you start looking at the problem instance, generating solution candidates, right? That's the data, that's the generator. Then perhaps you have some, normally, of course, you have some auxiliary predicates that analyze the generator. Because the idea is always when you model, that's how I do it. I assume that this generator gives me a bunch of atoms. Right? So I will have afterwards, I will have a bunch of atoms, of instantiations of a sign. And now I analyze it and I have to check things. So I may actually here then define auxiliary rules or whatever, and then do other checkers. And that's more or less how I do things, right? You put the generator and then you analyze it, and you can always assume that you have it, even though you don't know which it exactly is. It will give you all of them. Okay? Data, generator, tester. Okay, that's more or less what, yeah, I was just not using my mouse properly. So we now have 4 o'clock. Let's perhaps just look at the first 3 thingies. Satisfiability, just for those of you who know SAT and how do you do that. Then Queens and traveling salesperson, then actually just jump to the engineering part. Okay. Satisfiability, again, you all know satisfiability problem. And again, here we will do this more or less in CNF. So we have a propositional formula in CNF, and we want to check whether there is a model for it, right? So this is our formula here, already in CNF. So we have a conjunction of clauses. And now if we map this into ASP, first we have to write the generator. And again, by adding these 2 choices here, what we logically do, we add actually A or not A, and B or not A. No, B or not B. Right? This is what we do logically. But what we more or less then say, A and B should be treated over the open world assumption. Actually, these 2 rules will generate 4 combinations. A and B are false. A is true, B is false. A is false, B is true, and both of them are true. Right? If you only take this code here, will generate the 4 models, and then you write the tester here, which tests. It cannot be the case that A is false and B is true, because if this would be the case, this clause here would be false, and that's now the second one. It cannot be the case that A is false and B is true, because this would then violate the second rule, right? And just to summarize this, so the generator puts actually A and B under the open world assumption, that what I just described here. And the tester eliminates interpretations that violate the formula in CNF, but it's expressed negatively. Let's just check this, right? So let's where's my, let's now just keep observing what happens here. So we have this formula. So we translate this, we apply De Morgan ones, then we re-express here the negation, this negation and this negation as an implication. And you see this here is exactly what we wrote here as an integrity constraint, just to get this clear. Good, so this is just a little bit to show that how easily you can use ASP for SAT solving. And of course, you're not at all, this must not be a CNF. You can just you specify things in an arbitrary way, and then you just have to come up with an axiomatization of how satisfaction works, right? That does not mean to be a CNF, just for this example. Okay, now let's actually build an encoding from scratch, and let's do this in a very, let's say, well, in a very pedagogical way, right? So starting from the generator, then yes, Jacques.
Yeah, so if I do some SAT problems with this, in terms of performance, how does it compare with manually encoding the SAT problem myself and using a top level?
Well, it depends. It depends a bit about what you measure, right? So where you definitely gain is development time, because if you do it in SAT, you have to write somehow. You have to transform your original problem into Dimex, and you have to write a Python or C++ thingy. While here you can use the technology off the shelf. Then in terms of performance, well, of course, you have the grounding time will happen. So if you actually write if you take advantage of ASP and you write your problem in first order, so then of course grounding has to happen, and this takes time, right? But also your Python or C++ thingy has to do that, right?
Yeah, I was more meaning like the solver once discard the grounding part.
Yeah.
How does the ASP solver taking the grounding, the grounded program compares to a SAT solver?
Oh, I think it's at eye height. You know, I would not vouch now for the latest development of Armin Biere and Matt Soos and all the fancy solvers, but it's more or less, it has the same order of magnitude. Actually, I know quite some people actually who use CLASP as a SAT solver because of its functionality.
Okay.
And actually, you will see that when you just take CLASP, and actually you can also feed Dimex to CLASP, right? What you will see is when you look at the command level, if you do a minus help and take level 3, minus help equal 3, you will see lots of options, right? And this, I think, is one of the unique things about CLASP, that you can that you have a lot of, that is highly configurable. Okay, good.
Thank you.
Oh, you're very welcome. So N queens. So I think you all know N queens, right? So let's just jump directly in it. So we more or less want to put N queens on an N times N chessboard so that no two queens attack each other. The first thing we have to define is more or less the board. And again, I take now this approach. I think each of us would have done it differently. I just say there are N rows and columns. And again, since it's N times N, one could get away with easier representation. Let's just do it in such a way. So we define our N rows and N columns. Nothing. So if we give this, for instance, now to an ASP solver, and here you already saw that I was using the constant N, and you can, from a command line, you can then say, oh, you want to instantiate this N with 5, and then you call it, and then you just get these things expanded. This is very boring. It's just to build things up gradually, right? So you have 5 rows, 5 columns. But you saw at least how this works with the constant. Now we do a guess. We place queens. And again, we do this in a very didactic way. So we put no constraints on the on solution candidate. We just say guess the solution, and this more or less means here this is a choice rule. There are no restrictions on the choice, so it will actually enumerate the power set. So we would start from the empty set. There are no queens to putting queens, 1 queen, then 2 queens, and in an order that you cannot predict, and then eventually it will also have queens all over the place. So queens are placed in some arbitrary way now on the board. And here I just say I want 3 solutions. I want to enumerate 3 solutions, and the solutions that actually are generated. Yes, Camilo. Camilo? You raised the hand? Okay, perhaps by accident. Anyway, so we get three solutions. Here, someone has an echo here. Can you mute yourself? That looks good. Good. Anyway, so the first solution, actually, there are no queens on the board. Here we put a queen on position 1-1, here on 2-1. And again, these are just the first three that I enumerated. You actually see here, whenever class potential gives you a plus symbol, it says the search space has not been exhausted. There are still solutions pending, or there may still be solutions. So just graphically showing this, now this is the first solution, where there's no queen, and you see there's actually no queen here on the board. Second thing, there's a queen on 1-1. Here it is. Second, there's a queen on 2-1. Here it is, and you can you see a little bit how this goes. Now these are more or less the guesses we made. Now let's actually say that we want to place exactly n queens on the board. And again, let's do this didactically first. And I do this with an integrity constraint. And keep in mind, with an integrity constraint, I have to formulate it negatively. So I have to say there must not be a number unequal to n. Again, this is, one has to get used to it, and there are much better ways to do that. But again, just in this way, we can it's modular, right? We just add constraints and we don't modify, because you will see the more elegant way to do that. Actually, I show the in a sec. So anyway, this is the integrity constraint. So you take the queens, you count them, and it must not unequal n. And so it must not be the case that it's unequals n. This is the constraint that enforces this. I think I will do this. Yeah, that's actually the much easier way to do it, that you simply right away say that you want n of them. But you know, this is not modular. I now here I just added something, and this actually had meant that I changed the program. That's actually why I put this other one first. But this is normally the way you do it. So it says place exactly n queens on the board. And now again, we are looking at five queen problems. I just want 2 now, and here you now see exactly 5 queens on the board. That's the first solution. It stacked them all here. And then the second solution it enumerates is this one. This is all heuristic driven. It's not deterministic. So the order in which the solutions are given out you cannot predict them. It's deterministic, but you cannot predict them. So, and this is the second solution that you get. But you already see that this violates quite a lot of the constraints, right? We have here, of course, queens that attack each other, not to talk about the other ones. These queens attack each other, right? Also, these queens attack each other. So we still have to eliminate solution candidates that do not satisfy the constraints in the n queens problem. And now let's actually forbid horizontal and vertical attacks. And an easy way to say is it cannot be the case that in the same line, that's the same line, you have the same I, there are queens in different positions, and hence they attack each other. And the same actually for vertical attacks, right? So you have to have this inequality, otherwise a queen may attack itself. Good. So this is more or less the way how to forbid horizontal and vertical attacks. Then now let's run this program again. I just want 5 queen problems, no number given, so I don't make it 1. That's the solution that I get. Let's look at it. And here it nicely produces this solution here, but of course this violates one of the diagonal constraints. And now, of course, we have to add constraints that say, oh, there cannot be 2 queens on this type of diagonal and on this type of diagonal. That's what we do here. And this is actually, this is the formula that gives it to you. I will not detail that, right? But what you see is you make sure that on the same diagonal in this direction, there cannot be 2 queens. This forbids diagonal attacks. Let's just do that. So we now launch it. That's the solution that we get. And this is actually what is an output. And this is actually, as we can verify now by our eyes, a valid solution to the n queens problem. And again, this was more or less this. Again, I don't want to oversay. In a didactic way, you put the generator that guesses you a solution, and then you test the solution. And here we didn't define any auxiliary predicates, but normally you do that, and then until you have all the constraints added, and then you get the solutions out. Okay, so this is more or less this encoding can be largely optimized, because I have to confess, you know, ASP is declarative in the sense that it decouples the specification of the problem from the way it is solved. So you do not know, actually, there's no execution model, right? Like in Prolog or like in C or Java or whatever, right? So it's declarative in this sense. But, you know, if you give it one specification and another specification, they are logically equivalent. One may perform better than the other. That's also the same here, right? So in this way, we haven't reached the holy grail to make it completely declarative. Okay, this is now our encoding. And here, for instance, in encoding, you may come up when you're more experienced. I drop the row and the column thingy, right? This actually combines the generator and the constraints on the horizontal and the vertical text. It more or less says, let's say I pick a row or I pick a line, and I look at all the queens that are in there. That I pick, let's say, I pick a line, and now I look at all the queens that can be positioned in this line, but only one of them can be put. So in each line, only one queen. In each column, only one queen. That's the second one. And then here it's the same thing with the diagonals, again with this enumeration schema that I didn't detail before. It says if this gives me all the queens on diagonal D, and it cannot be the case that there is more than one queen on the diagonal. This goes for both diagonals. And this is actually quite performant actually. So for instance, this is now a Queen's 5000 problem. I used to solve that with a Klingo version or class version 4. And you see, I more or less this ran an hour or so, right? And after an hour, I got a solution. I didn't print it, right, because that had spoiled it. But one thing that is interesting a little bit to see, right? So you see here, I launched this now with a stats option so that I see all this output. Then here I choose another pre-configured version. -Q says I suppress the printing of the answer set. And so you see, for instance, this is the net solving time. So it took 3,760 seconds to ground and solve. This was only solving. So the remaining time, I will not do the math now. Subtracting the solving time from this gives you the grounding time. Then you see here the choices and here the conflicts. And here you see actually that a lot of choices just work. There's not so much search going on, right? Because it made a lot of choices, but it had only 3,400 conflicts. And what is also interesting, when it read, it had originally, let's say, 75 million atoms and 100 million rules. But after actually equivalence processing was happening, things boiled down to 66,000 constraints and only 25 million variables. Anyway, so just to show you a little bit what is happening and how far one can go with it, right? Okay, so let's now look. Yes, Jacques.
Yes, there is a question in the chat, and I'm gonna follow up on that.
Oh, I didn't see that.
In terms of ease of modeling, this first point, and the second point, requirements of memory. How would this approach compare with doing the same problem with CLP-FD or Minizinc with pure CSP?
I can't tell you now, but I think we never compared it. I more or less, I just showed this now as an example for the perform. Well,
I mean, not necessarily on the Queen problem, but in general. I mean, you know, what are the pros and cons of those three families, like CLP of FD or CLP of R, or what CLP of X, let's say, on one hand, and then the other is ASP, and then the third is the main CSP with Minizinc or something like this.
Yeah. First of all, I think the problems. So, for instance, we have a FlatSync compiler into ASP.
Okay.
But then actually we don't run ASP solvers, we run our hybrid solvers, because often enough the problems where a constraint solver is good at, they have variables over integer domains, right? And lots of integers, unlimited, right? But in ASP it's mainly a Boolean thing. So again, right? So if you translate a problem with this, which has a lot of numbers inside, where your variables are over numbers, CP solvers are pretty good, and we do not use pure ASP to solve them. We use a hybrid ASP solver that has either CP propagators inside, or that or other things. So the thing is, it's hard to compare. I think on purely Boolean problems, I think ASP and SAT solvers are just much faster, right? Because they're optimized for that. So I hope this was not a direct answer. I agree, but I hope it sheds some light.
Well, it's a hard, very general question. So it's a sweeping statement question. But
yeah,
I was just curious because I'm just discovering CSP, and I'm used to CLP of X and Ninizing. So for me, it was a natural question.
Yes, thanks anyway. There's no clear cut. Anyway, one, just to have to give you another answer. I was mentioning that we have a company, and in this company, I think 80% of the applications that we do with hybrid solvers. So we combine ASP with difference constraints, or we can combine ASP with CSP propagators or stuff like that, because you need things from both of these worlds. And this then really performs very, very well. And the interesting thing is, when we are out in industry with a company, our competitor is MILP. So there is Gorobi out there, there is Cplex out there. So you don't see actually industry. At least we haven't come across any other solving techniques there so far. Okay, good. Okay, so traveling salesperson. I think this is interesting because it really sheds some light on the advantages of ASP. So traveling salesperson, I think everybody more or less knows. You have a set of cities and distances among them. Oh, the two participants raised their hands. Okay, guys. Go up. Tell me. Hello? Questions? Okay, so I since nobody speaks, I just continue now. Okay, we have a distances among them, or a weighted graph, if you, and then the question is, what is the shortest possible route visiting each city once that goes back to the original origin? So there is, of course, here this is actually a Hamilton cycle problem, but you have optimization because you want to know the shortest such route, right? And this is used very much in industrial applications. So here's just an example. So I did this in terms of cities. So let's say we have city A, B, C, and D. And we start at city A, and then we have roads from A to B. The distance is 10, and the same for the other roads. Okay, now this is more or less our problem instance. And now we want to write an encoding that works for all these problem instances, and here's how it goes. So the idea is we look at all the roads, and we can now choose to travel on such a road or not. So here I just did it in a way that I have an instantiation. Let's say I go from A to B. I ignore what is here. That's the anonymous variable. I ignore that. And then I can choose whether I travel from A to B or not. And this is my choice rule here, right? Okay. Let me just erase this. And now I have, with this here, this is my generator. Now I assume that I have a solution candidate at my fingertips, a guess. Travel from A to B, from C to D, and now I have to evaluate, does this constitute a valid route? So the first thing I do, I analyze it. So I say, okay, I take the start node. In our case, this was A. Now, if my solution candidate has chosen that I travel from X to Y, right? We know that X is now A, but then I visited this other guy. Right? So keep in mind that I don't derive that I visited the original node because I want to come back to that guy, and so I have to derive it, right? That's the idea. That's how I get the cycle thing. But the idea is, if I now travel from my start node to another node, I visited the other node. Then recursively, if I've shown that I've visited a node and I decided to travel from this node elsewhere, I also visit this guy. So this gives me all the cities that I can visit with the solution candidate that I have guessed or generated. And now I analyze this. First condition, it cannot be that there is a city that I have not visited. And this actually gives me this cycle, this more or less that I can go back, that everything has been visited. But now I also need to make sure that that I visit a city only once. And here this constraint says it cannot be that there is a city X where I exited twice or more. Because if I travel from, let's say I take city 3, right? Oh, there is no city 3. That's so sorry. Let's say I take city B, and now I look at all the solution candidates where I travel from B somewhere. And if there are 2 or more such ones, that doesn't work, because then I went in and went out. I went through this several times. And the same actually when I go into the city X. There cannot be a city X to which I traveled twice. Now this is already an encoding of the Hamilton circle problem. And what is really special about this, look at how easily you can deal with the recursive condition here, right? This is transitive closure. And transitive closure, normally in a monotonic framework, you need to second order. At least you can always hack things together or have something fancy for a specific problem. But in general, in a logical sense, to capture transitive closure, you have to go to a second order logic. And this actually works here thanks to non-monotonicity right away. That's actually very nice. And then, of course, to make this optimum, you add to the objective function is then whenever you travel from X to Y, you pay the price, and this gives you then the shortest path. And that's then the traveling salesperson problem. And you can also do this with the minimize. And then if you launch this, that you give to Klingo the encoding and the instance. It reads it, it solves it, it finds a first solution, and actually it will not stop here. But this solution has value 100, and then internally it adds actually a constraint that says you want to be better than 100. So it looks for a better solution. It finds actually one with 95. Then it looks for a better solution. It doesn't find one. It knows that the last solution was an optimum, and that's the way it goes. This is the default behavior of Klingo, where it actually works with branch and bound, simply that the user sees something. Often enough, it's better to work with unsatisfiable core-based optimization, but there you don't have such a successive output. Okay, anyway, so this is more or less how this would then look like. Okay, I would now, this is perhaps yet an encoding that is perhaps a bit better. I would now skip the encoding session and go directly to our engineering part, if you allow. So let me just do this with the oops, I was there. Because you have all this rest, you have all the rest here. Oh, I have to go through that like this manually. So you can also just look this up. So let's now look at the second big part. This will more or less be the part that I want to show you until the end of this tutorial. Now, what you've seen so far is more or less the cozy ASP world, right? That more or less you, as a computer scientist, as an academic, you sit on your model, you launch it on the shell, you get something out, you're happy. But once it comes to applications, there are different requirements. First of all, you may want to modify things, or you need to control things. You have to incrementally solve something. You have to add other constraints, and that's more or less the part I want to go through right now. And more or less, the idea is that you take ASP. And from a general perspective, what you do now, you combine it with another language, right? With this code in another language. If you want to add a propagator for different constraints, you write this, I don't know, in C++, in Python, you add it. So you have to combine Python or C++ code with an ASP system. Or incremental planning, right? You want to augment the horizon. You need to write a control loop to do that. You have to integrate this in the solver. Again, this is written somewhere else. And that's the really cool thing. And I think in particular for testing, you can also combine ASP with ASP, because you can do metaprogramming. And that's actually the first thing I want to show you, because often enough you get a first idea on how things work. That's the easiest way to do it. It's very easy to do things right away in ASP. Okay, let's look at it simply because I find it so cute. And we use that a lot actually also to do rapid prototyping. So you can see, you can actually find the techniques that I'm describing here in the sequel in this paper here, and I also have it in the bibliography in the end. It's how to build your own ASP system, and there actually we detail this, detail all the techniques that we'll follow now. Let's start with metaprogramming. So This is a meta program. This is an ASP solver written in ASP. Isn't that cute? You see, you more or less, you have a couple of lines, and if you now want to extend your ASP solver, well, you take the meta interpreter and change it. Let's look at this in a bit more detail, because of course this is not really understandable right now. So this is my easy logic program. Again, I just do this now in a propositional way. This is my easy.lp, and I can of course solve this right away with Klingo, right? I call Klingo. I have here my file. I want all stable models. I get one where C is true and one where A and B is true. Now I can do the same thing with metaprogramming. How does that work? So I take the same program, and now what I do is, in the first step, I use Klingo just as a grounder, and I reify my program. So what happens here? What I get here in this part here, I get a representation of the ground program as facts. So now I have a representation of easy as facts, and this is actually here. This output comes here, and then I combine it with my meta interpreter, and I launch Klingo. And this is how metaprogramming then works. And that's all I wanted to show you, because we can't really go into details, because I think the thing that really interests you guys is how to combine this with more sophisticated programming language. And in this way, actually, you can, here in this meta LP, you decide how you interpret language constructs. And actually, the first application that we had, we wanted to do other types of optimization, because when you write a weak constraint or minimize statement, it's interpreted as being optimized with minimizing the sum of something. But with, oh, we would like to do Pareto, or we would like to do a subset, right? And we did this with metaprogramming. The idea is, whenever you reify, then you see the fact of metaprogramming, then you add ASP code to it that implements Pareto or that implements subset, and then you have a solver that just by metaprogramming, where you more or less redefined the objective, the evaluation of the objective function. That works actually like a charm. Again, in the paper we have this really detailed. I just wanted to give you a glance on that. Okay, now let's come a bit more to the more serious stuff, controlling ASP. So actually, the first thing to see, and this is more or less talking about the API of Klingo, there are 3 alternative ways in which you combine ASP now with other languages. Now I talk about Python or C++ or Rust, and there are APIs for all of them. Here I just talk about Python, but again, as I say, right, there are many others out there. First thing is to simply add things as an embedded script, then to more or less to completely go to the other programming language, where you more or less you import just the ASP solver as a library, or you actually take Klingo as it is, and you override, you derive certain structures, and you override certain methods. And that's actually when you want to derive your own ASP-based system. But here are some examples. So let's say we want to get the divisors of a number, right? And here, this is now, I have number 3 and number 6. And for each of these numbers, I want to get here a binary predicate where I have, this is my input, this is the 3 and the 6, and here I want to get all the divisors. And this add here will actually call an external function. That's a common construct that's also like this, I think more or less similar in DRV, if not the same. And the result of this is this. You want this, right? You want that 3 is divisible by 1 and 3, and 6 is divisible by 1, 2, 3, and 6. And this is just a shortage for dividing div of 3, 1 and 3, 3, and these are 4 facts. This is just a compact representation of it, but that's also actually how the result is returned. That's what you want. Now we look at 3 different ways to implement that, to more or less implement this divisors thingy. Okay, first one is very easy. You just add, you more or less just take this one and add this to your encoding. You would add it here. This means embedded scripting, right? You just, here in Python, you say, oh, and now here comes a chunk of Python, and here's my implementation of the divisors, right? And that's it. And I think for such a case, for the divisor thing, I think that's even the best solution. Now let's look at the more sophisticated. Yeah, okay, let's just see it. So we have here now the This is embedded. That's this file here, just that contains this. And here we have example, right? These are the two files. So we give example and embedded to Klingo, and that's what we get out, right? So we have here the divisors of 3, and here we have the divisors of 6. Okay, that's very easy. And normally you use that exactly for such easy calculations where you say, you know, ASP is about solving combinatorial problems. If you have a problem where you want to calculate, don't use it. It's taking a screwdriver to hammer on a screw, on a nail. Okay, then here's the one where the idea is that you import, that you do everything more or less in Python, right? So the idea is you import Klingo, then here's your divisor function, and then here you just run it. So what you do is since you have imported the library, you generate an instance of the solver. This is now, and this is a solver object, and this is now saved in this variable CTL. You can call this variable Frank or Michael or whatever. I just call it CTL here, right? Then you do all this by yourself, right? Then you load the example file that we've seen before. You ground it, and this is more or less the base program. You ground it, and then you solve it. But then you have to deal with everything by yourself, right? There is no environment that does it. And then you have to print it, and here you use the onModel printing function. That says whenever you find a model, you print it, and this is now the Python print. So very, very, very rudimentary, right? So this is how this works. So you more or less call Python, you call the module thingy, and you get this output. But you see, this is now the output of the print of Python, and you have to care for everything yourself, because now you move to the world of Python and you just include this as a module. That's the embedded script. Now the third thing is that actually what you do is you work with Klingo's main function, but you override, you derive everything from this class, and then you override certain methods. And this means whatever you don't override, you get for free. So more than everything we look afterwards like Klingo, just that you override certain things. Okay, how does that work? First of all, just for illustration, you want to build a system and you want to give it a name. It's called example, and it has a version number 1.0. And these things will then be handled by Klingo afterwards. Here's the divisor. And now what you do, you override the main function of Klingo. So this is now the main function, but now you do you say what you want to do. You look at, well, more or less this is more or less you handle the input, right? You get the path where you are, and you can load the files, or you can read from standard input, and then you ground and you solve. But now what you did is more or less, again, you took Klingo infrastructure, you added the function, and now you override the main function, because now actually it will when you launch here the ground and the solve, it will know about this divisor. And actually this function will be executed when grounding. Hence this context here is important. But again, I'm not the Lord of Python here, so I think many of you can do better programming. But now actually what happens is you use Klingo's infrastructure, and as you see the output, you call, of course, Python, you call the original file, and now the AP, this is this file here. And now things look a little bit like in Klingo, because you use its infrastructure. You see, that's the name of what you described. That's the version number. And here it uses the printing and everything more or less that you have not overwritten from Klingo. And that's actually, this is more or less the way how you write your own ASP-based systems. So again, there are these three alternatives. One is this embedded script, which you mainly do if you want to outsource small calculations and want to stay within the ASP. Just you say, this function I better do myself, and I do it quickly in Python, and then you have it in the same source. Well, if you want this. Then the other thing is, that's actually the first one, embedded scripting, right? Then module import means you really go to the world of the programming language, and you use Klingo as an engine for solving your larger project, right? So Klingo is used as part of a larger project that you are doing anyway. So you get the you get all these high-level functionalities and all that, but the application, what you are writing now, is in charge of the control flow, of output, and all that. The third thing is, if you want to build a system, if you want to customize a system that is built on top of Klingo. And again, this is similar to the module output, just that you stay within the architecture of Klingo and you only modify what you want to modify. And actually, this is exactly how we write nowadays all our modification. There's Klincon. This is ASP plus CSP, so actually arithmetic constraints over finite integer domains. That's Klingo DL. That's the version that augments Klingo with difference constraints. That's the epistemic ASP solver, where you can reflect about the answer sets. And Terlingo, this is what I mentioned at the beginning, our extension of Klingo with language construct from linear temporal logic and from linear dynamic logic, right? And they are all built with this application class in this way. So these are more or less the three cornerstones. And we will more or less use this third option now in the remainder of the course. Now let's first look at multi-shot solving. And I will now actually jump a little bit, because I will walk you through code, but only point a little bit, because first of all, we only have now 20 minutes left. And, you know, I don't think that it's assisted code reading is the best thing that I can do. So anyway, multi-shot solving allows for solving continuously changing logic programs in an operative way. What it means, operative means you have you create a solver object. This solver keeps running. You send logic programs to it. You may want to remove rules, and you interact with this guy, right? And this solver keeps running. That's more or less the idea. And somehow while single shot solving is just ground and solve, that's what we did before. Multi-shot solving is, well, you ground and solve. You perhaps ground several programs, you solve several times, you want to iterate the whole thing, and you can do a lot of things. That's a bit the idea, right? There are applications, and more or less the idea is that for all that is, you take ASP and you add control around, and the control comes from the API that gives it to you. Good, let's look at this. There are actually two language constructs that more or less do the trick. The first thing is, there's a program directive. You can now say, oh, you can structure your ASP encoding. You can give subprograms names. And think of game playing, right? So you may have actually then a program where you say, oh, this is more or less how a player acts. So if you play tic-tac-toe, one will do the crosses, the other one will do the circles, right? And you will instantiate this once for the circle player and once for the cross player, and at each time step, right? This will more or less give you the transition system in tic-tac-toe. And then you say, these are the rules, and they all correspond to this play thingy, and I can instantiate with different players at different time points. The default of this is the base program. So all the rules that are not in the context of any program declaration are put in the base program. That's more or less the default, right? Good. Then look at this here. So more or less, this is an ASP program, and here you see we have this declaration. So and this more or less means everything that follows now until the next declaration belongs to the subprogram ACID K. And here's a new declaration, which is base. It's redundant. So well, you more or less here you have to say that you are out of ACID K, and you have to say now you're back in program base. So in program base will actually contain A of 2, and also everything that is not preceded by a program declaration like A of 1 is also in the base program. Okay, so I call this now chemistry.lp. So if we now do it just by importing things, just to make things easy, we import Klingo, we generate a Klingo object. That's now our Klingo, the variable that holds the Klingo object. We load our chemistry thing, we ground it, but here we ground only the base program. And then we solve it, and we print the solution. And what we get out is then what belongs to the base program. Look at this, it's A1 and A2, and that's what we get. Okay, because after all, yeah, I have it here again. But this is not preceded by a program declaration. So it is put in the base program. Here there is the explicit program declaration base, so it is there. Now let us do the same thing, but not write base here, but use ACID, but now say, and the argument is 42. Well, now we actually get B42. Why that? Well, look at this here. This gets instantiated by 42, this constants here. So we get a 42 here and a 42 here. And of course, here B42 is a fact, so we get this here. But this rule here, because we have, we have no, since we do not ground base, the base program, we have no instances of A, hence we get no instances of C or whatever, right? So the only thing that we get when we ground acid for the value 42 and solve it is B42. Actually, there's not really solving going on here, but good. So the other thing is that is very handy actually is to define atoms as externally defined. And the idea is normally in ASP, all the atoms are defined by rules, right? But here the idea is to say, okay, to distinguish an atom, that this atom here is defined externally, it's controlled from outside, right? And that may be, I don't know, if you have a board game, that may be a position in the board game, and certain positions are now active or inactive because you want to control this from the outside, or sensor information, right? There is sensor information and there is no rule for this, this just drops in suddenly, or it goes off, on and off, and you want to control this from the outside. And for this, actually, you have this directive external. And again, in our game world, let's say with tic-tac-toe again, you may have an external that something is marked, right? Let's say tic-tac-toe is played by two solvers. One solver plays the X's, the other solver plays the O's, and then one communicates, I make this move, and then this guy receives this move, but it's external. It's determined by the other solver. And this is more or less what you can do in such a case, right? You say for all the fields, you have for all the fields, they can be marked by a player at a certain time point. That's the second mechanism that works like a charm in that. And then what these external atoms are, they are protected from program simplification, right? So it's not that, and then you can assign truth values to them via the API. Once you add later on a rule, they get overwritten and eliminated from the system, and they can also be permanently set to false, which so I don't need you anymore. So go, then the whole thing can be things can be simplified. Let's look a little bit at that. So this is again our program that we had before. And now I add more rules to, I just say, okay, here there's an external definition and another rule that belongs also to the ACID program. And now the idea is a little bit, if we now throw everything together, right? We will actually get, so we have A of 1, we have A of 2, and then we also get here instances for this guy. So once we have the C, we generate some external here. And then depending on whether this external is true or false, this rule here will be activated. Okay, so now if we ground both again, if we put all this together, ground base and ACID 42, we get here an instance for 1 and for 2, and here for 42. So this means here we get two instantiations and we get two externals. We get D of 1 and 2 and 42. Two externals, and we can control these two externals accordingly. Depending on whether this external is true or false, this atom will become true or false. Let's just look at that. Again, this guy is now chemistry external LP. So what we do is we create a Klingo object. And now we load our file that we have before. And now we have two alternative ways, right? So now we ground everything, and now we solve once, then we change the value of it and we solve again, and we look at the output. So let's look at this in steps. So we load our program. Then we ground the base as well as the ACID program for 42. Everything is now inside. And now we solve and print the model. So at the beginning, the default value of the external is false. Hence, we will only get A1, A2, and we get this C142 and that and B, this here. However, in the second call, what we do here is we say that D of 242 is true. We also get then D of 242, and we get E of 242. So keep in mind, so what happens here is we have two externals. This guy becomes true, so we also get this guy. So you see, in this way, from externally, so this is more or less your API call. From the external, you say, now this atom becomes true. Then you solve again, and the constraints in the solver, the program hasn't changed, and you now get you can also derive more information. So it's not only that the external atom becomes true, that you're actually setting here to true, it's also that suddenly you can derive more information and this becomes true. So this is more or less how this mechanism with the external works. And the cool thing also is here I made something true, but if you have a rule where an external occurs in the body, this rule is only active if the external is true. If you make it false, you more or less make this atom fall and the rule cannot apply. This way you can actually even delete rules with this external mechanism. That's actually, if you do multi-shot solving, these externals are very, very much used in solving. Here's another usage of the incremental solving. So let's look at a actually we have it's a little bit like before, right? So let's say we now want to enumerate numbers or whatever, right? And we do this incrementally. So we have a base program, we say P of 0. Then let's say we have a program that we call step T, where we say, oh, P of T is true if before P of T minus 1 is true. And now we want to check whether we are up to 42. So the idea is that we declare such an atom here, query of T, as external. And this is something that you can then manipulate from the outside. And then you say, then in your check program, you only succeed, you only get a model if it is not the case that P42 is false. It is if you get P42. Now the thing is, you see here, this is conditioned with this query atom. And the idea more or less is that whenever, so you first do the whole thing for 1. Right? And then you have query of 1 and you have query of 1 here, and then you make this true. And then this integrity constraint is true. Well, you don't have 42, so okay, bang. Then you augment the whole thing and then you try it for 2 and for 3 and then you can always play on the truth value of query of 1, 2, or 3 to actually have this query here active or not active. So by making this atom here true or false, you decide via the API whether this query here is active or not. And that's actually the mechanism how you can easily with externals and these programs then work incrementally. It's of course there has to be Python code around it that says now you ground step for 1, step for 2, step for 3, and we will see that in a second. Okay, this is actually the code, and again, this is not meant for you to read. What we will actually do is we will look at some pieces of it. So first of all, we look at the main procedure, and we will look at the options. So I now want to show you how we can solve such a problem. How we can solve that. There is something pre-programmed in Klingo actually, but you can do this by yourself, just by Python or C++ programming and the API. Okay, now we look at just some, so here we look at something, just a feature that allows you to extend your application by registering options. Again, it's perhaps a bit sidetracked, but you can, if you now want to write an incremental version of Klingo and you write this thing, you can actually want to give options to the user. So this is actually, there's this register option function. You have groups of options. So this is now the inc example options. I just named them like this. So there is an imin thingy, and it has a minimum value, and sometimes and this is the default argument that you see. And here there's an imax and istop. And just to show you what you can then do is, you can, if you then use, this is the inc pi. Keep in mind this is this unreadable program here. This is this guy here. And if you call this with -- help, Klingo, you will get Klingo options, but also your option that you are now about to define. Okay, so I will not go further detail, just to show you this convenience feature. Now let's go to the main function. That's actually the real interesting part. So what we do is we override the main function. And now we have a loop here that more or less increments the value of t until we have satisfied our goal. So how does that work? So here, first of all, we have we load the files and all that, and what we do once we have loaded all the files, then we add here this check program. Just as a convenience, we add this ourselves, so the user doesn't have to do that. So we see we add a program that is called we add something to the check program that has a parameter, and that's the source code of this here, external query. We've seen that. So this is added here as a convenience feature, right? Good. Then we say, oh, we are now at beginning, we are initializing things, we are at step 0. So we want to solve incrementally. Let me just erase that. And now actually let's just follow this while loop, right? And this while we have given the criterion. Let's say we iterate until something is satisfiable, right? Until we have set the I-stop criterion to sat. Let's just look at this instance now. We iterate until it is satisfiable. Yeah. Anyway, so we are now at step 0. And what we do is we have here a variable that accumulates the program parts. And the first thing that we do is we append to it the check program for the current step number. So actually what we do is we instantiate this program here. Step number is 0. So this actually gets a 0, right? And this is put in this program now. Now then again, we take the base program and we also append the base program to our parts variable here. And so at the beginning now we have the base program. So we have not done any step, right? We just look at time point 0. And then we take the base program and the check that contains the query. We ground all the programs in the parts variable. We set this, we activate the query because this is an external, so we can activate it by setting it to true. And now we solve it. And we increment the step. Now we solve it and now we analyze the result. Let's say the result was unset, right? Then we go again through the loop, but now the step is 1, right? So we enter this loop again with step 1, parts variable set to 0. We add again the check here, the external, but now with the value 1. And now since the step is greater than 0, the first thing that we do is we set the last query variable to false, right? So we release it. We say even this is permanently be set to false. You can delete all the information by cascading it, right? And then you append the step program for 1, and you make the actual query true. This is now at step 1, and you solve it. Now what is now in the solver? Now from step 0, we have the base program. We also have the query for step 0, but we just actually deleted that. And we now have the query for step 1 and the step program, right? So base program and step 1 plus the query for step 1. And this will continue like this until the query is satisfied. I know this was a bit hand waving, but I think this is code that you have to look at anyway. This is more how you can use the API to do that. So we now have actually only 8 minutes left. So more or less if you do that, right? So I took here a Towers of Hanoi encoding and instance. And if you then launch it, you get here 15 times unsuccessful solving. It tries to solve, it doesn't work. And just with when you have looped 16 times, you get a model for this Towers of Hanoi problem that I haven't shown you now, where this here is the solution. Okay. Now, optimization you can implement in the same way, but let me skip that in terms of time constraints, right? You can do branch and bound optimization. And here I also will go through, I will not go through, but these are the 2 methods that I would have detailed if I had the time, this one and this one. And then you see a little bit what, if you then launch this script again with the Towers of Hanoi thing that I haven't given you, but that is actually in the paper, you see that it wants to find an optimum plan. And it does optimization. It finds first a solution with 17, then with 16, and then with 15, and then the optimum is found. But this is again done by this Python script that is here, right? This is doing branch and bound optimization in a customized way. You define how the solver should run, how you add constraints, remove constraints, and stuff like this. The reason why I'm rushing is because I want to come to theory solving, at least. And this is now more or less the way how you augment this. So what you've seen with multi-shot solving is how you can control the solver from the outside. You can add ASP programs, remove ASP programs, but it's all ASP world. It's just more or less how you control the solver. You can do optimization, for instance, or incremental reasoning. Now, how do you augment the inferences of the solver? That's what theory solving is about. And what you need to do actually is here in ASP, you really have to, you can't just take an SMT solver and everything works. No, you really have to take the whole workflow, which we've seen before, right? And add theory handling to all of it. That's very important to see. And the big problem is, of course, that the new atoms that you get, because you also have to extend the modeling language and so on, the solver doesn't know what these guys mean. Only the theory propagator in the end. That's of course the big difference, right? You ground modulo theos, you solve modulo theos, but the new atoms that you get, you don't know. Okay, so let's look at the solving process. So the idea more or less is that we have the same solving process as before. It's just that we have to extend all 4 aspects more or less with the new theories that we have. Input language, grounding has to know about it, solver, and stable models. How do we do that? Okay, first of all, this guy, we now look at the variant where these guys are put together, but that's not so important. So this is Klingo's approach. So of course, theory solving is added to the grounder, to the solver. You get not stable models, you get theory-specific stable models. Your input program has new language constructs. And where do they come from? Well, this is the opening key. You specify a grammar. So more or less, Gringo has a grammar formalism in which you can specify new types of atoms that the grounder will know how to ground, but he doesn't know the meaning really of them. And then the solver can capture their meaning in the end, right? And let me just show you this very quickly because we're running out of time. So this is, for instance, the grammar specification for CSPs, right? And you then have you have a domain predicate, some predicate, show, all distinct, minimize, and then you can specify if you have the send more money example. I think most of you know that, right? You want to solve this problem here, and there's actually only one solution where you replace all the numbers by 1 digit. This is the solution. So this is more or less how you can do this in ASP modulo constraint solving. So you augment ASP with the grammar that you've seen so far, and then you see here you have a sum constraint, and here the idea is that the send is a digit. This is actually the first number. It's send. This is the second number. It consists of the variables mo of the more, and this is the sum, which is the money. That's the way how I encode it. And this is more or less in the base, right? So the first digit is the first digit is the y. The 1 multiplied by 10 is the e. By 100 is the n, and so on and so forth, right? And then you will use this to instantiate this sum constraint here. And once you do instantiation, and the thing is, look for instance here, this is ASP code. So this will be expanded by the solver. This here is in the scope of a theory thing. The solver doesn't know what this means here, so it doesn't expand it. So if you now ground this, you get this here. So you see, for instance, here everything has been expanded, but here all these theory-specific things have been left intact, and only the ASP part has been expanded. And the way to solve this send more money problem is just to say, well, you build the sum of the send and the more, and then you subtract the money from it. And if this is 0, then you've solved the problem. And then you have to say that all of these are all distinct, and you want to show them anyway. So this is how this then works. Then you launch Klinkon on that, and then you get a hybrid answer. This is more or less the ASP part of the answer. And then here this is the theory part, which is the assignment, the solution. There is only one, as you see here. There is none, because I asked here right away to give me all the answers. There was only one. Okay. Yeah. Then propagation again. This is a bit more delicate. The idea is the propagator actually has a very clean interface. So how do you implement the propagator now that actually interprets these theory constraints? And actually, this is the interface here. So there are 4 methods that are important. One is the initialization, where you want to tell the solver, look, whenever this atom or this atom changes its truth value, I put watches, tell me, and then I have to do something. And then you have, whenever you propagate, whenever a propagation happened that gave you new values on the theory atom that you watched, you are called. And also when backtracking happens and values are taken away. And then last but not least, to do a last check, for instance, is it really a solution? There's also this is the real interface that you have to program, and the rest is just a bit the whole what comes with it. And this is actually a very simple propagator that just prints dots, but I will not go in detail. And heuristic solving, unfortunately, we don't have the time, so let me actually wrap up. Yes. I jump over applications. So here we are, wrap up. I'm sorry that I had to skip so much, but yeah. Good, then, as I mentioned, right, all the tools that you've seen are completely open source, and this is all held together at potasco.org, where you have a GitHub underneath and you can look at all that. So we also have, meanwhile, a commercial branch. Let me not make too much advertisement here. I don't want to steal your time on that. What are the take-home messages? So first of all, I think the benefits are really start with this distinction between what is your problem? Tell us what it is, describe it on a high level. That's where the knowledge is. And then you have a generic engine, a solver that knows how to find the solution, right? The important thing is the knowledge is yours. That's more or less the users, and that's where it comes from, right? But more or less, ASP is a technology, and you still have to model it, and specific products or solutions emerge only normally from cooperation, from combining ASP with your problem. This is more or less some of the benefits, why you should use it and what you can do with it. And then from a nutshell again, so ASP is not only a solving paradigm, it's a modeling, grounding solving paradigm. It has all these aspects to it. And it combines actually technology from databases, logic programming, KR, and SAT, or if you want to be very exact, SMT, where you have, of course, the ASP-specific inferences as well as others on the side, like optimization and stuff like this. And again, all this is bundled here at Potasco, and it's a lot of fun, right? So, and let me just stop at this point and perhaps take questions if there are. At least we are good in time.